different direction.
What do you think about Simon Sullivan and later Schreiber, the work on differential cohomology?
Oh, yeah. I mean, certainly Ernst Schreiber's a mathematical genius in some sense.
Yeah, me too. I think
I haven't
Schreiber
dove
too.
in extremely great detail. I've actually been in email contact with him recently. I saw his talk where he had his view on M theory to some degree. So, I mean, yeah, it seems like good stuff. I mean, at the end of the day, I'm also trying to talk about the real world. I mean, to me, I think the point of physics is to talk about the real world. So, I mean, he's almost too mathematical for string theorists.
Too much math.
I mean, I like math too.
I'm an algebra geometer. I study the highest kinds of abstraction. So
That's really cool.
I like how Schreiber formula. What does it call it these days? Cohomotopy, I think.
Yeah, well, there's like homotopy, and then there's cohomology. Yeah, I mean,
I think it's specifically called cohomotopy because homotopy you're taking the mapping space from Sn into something, and then now you are taking something into Sn. I think that's how it works.
Yeah, he has an NCAT lab page on cohomotopy.
Yeah, Hypatia. Yeah, drop some links, Hypatia, drop some links so that I can show it in the stream, and then let me kick it off real fast so I can like introduce them and everything, and then we'll get into all the cool stuff. Cool.
Yeah.
Okay. All right. Welcome everyone to the Golden Hour AMA podcast. My name is Dr. Gold. This is Actual Education. I'm joined by my very super awesome best friend. I've been your best man, I guess, for a wedding, right? That puts us like on tiers of friendship. His name is David Chester, and he's a quantum gravity researcher. So yeah, nice. I'm gonna have DC introduce himself. We'll give a little bit of a background of who he is, what he does, and then we'll hop into some questions that you guys have asked. If you have any other questions that you want to know about, please drop them in the chat, and we'll get them on the docket here. So yeah, DC, maybe tell us a little bit about yourself, like who you are and like what you do.
Yeah. So I originally just I ended up getting into MIT for undergrad, which was very fortunate to have that
MIT's
experience. And while I was there, I was deciding what I wanted to do, and I eventually felt like physics was kind of my calling. And I really was initially motivated by unification, pursuing unification of the fundamental forces of nature, and that's kind of one of the bigger problems, which is, okay, we have quantum mechanics and quantum field theory, but then we have general relativity. So I was my hypothesis since like freshman year of undergrad was that there should be a way to apply Feynman diagrams to general relativity and to quantize it. And really, to be honest, I haven't published that much work that's really on quantum gravity, but I was able to go to UCLA for my PhD, and there I worked with Zvi Byrne, and he really is one of the leading experts in scattering amplitudes for quantum gravity. So I learned some things there that were very interesting. And yeah, I mean, it was very encouraging because basically I got denied from every graduate school except one. Because
the best one, though. That's how we met. The best one, UCLA,
That's how I met
Geo. The best one, dude.
Yeah. So when I was there, it was basically it was fortunate because my PhD advisor had the same perspective as me, which was hard to find because now at this point there's kind of string theory and there's loop quantum gravity, and that's kind of perceived as being the approaches to quantum gravity. But in my opinion, those are both really just kind of ripping off quantum field theory at the end of the day. So that's just my perspective. So
hot take.
Yeah, my advisor was into quantum field theory, and he actually figured out a few years ago how to get some additional results with graviton scattering. So, and then from there, I also was an entrepreneur for a little bit. I got into data science for a bit, and then I got my PhD. I did the data science thing for a startup for a year, and then I ended up joining this research group, a nonprofit called Quantum Gravity Research, and now I actually am doing some basically as a research consultant for this team that's looking to get into alternative propulsion. So
alternative propulsion.
That's a little bit about myself.
Yeah. Yeah, dude, we got some dope questions. People are asking about like UFOs and stuff, right? I'm really excited to get into your newest stuff with like anti-gravity. So yeah, this is a big complicated topic that I know like the kids are very interested in. They're like, whoa, like what is quantum gravity? So we'll try to, I guess, put it down into, explain it on their level
terms.
Exactly. But then we could also take more advanced
sure.
questions. Like Hypatia's a very high level math person, and I'm sure, they can talk the talk, Monkey says I didn't ask about, well, some of you guys asked about UFOs. Okay, sweet. Nice. All right, let's see what our first question is. Our first question here is from Jamarcus, and he says, what is the hardest challenge in figuring out a solution to quantum gravity? And what are your thoughts of the possibility of a graviton as proposed by string theory? Also, in general, is research in quantum physics a job that is profitable enough to live a decent life? That's a good one, right?
Those are a lot of great questions. I mean, overall, the challenges are really finding solutions. I would say, like, finding exact solutions is very difficult in general. So even if you wanted to do neutron star scattering, you have these two neutron stars, and they're at extremely high energies. They would eventually collide, and these neutron stars have a finite size due to quantum mechanics. So they're made of these neutrons, and there's this degeneracy pressure from quantum mechanical processes. So if they collide at enough high enough energy, it's combining gravity, obviously, because these things are extremely massive. But then if they're at high enough energy, the quantum effects could interact as well. So I mean, that's kind of the holy grail, I would say, in terms of what is challenging is to actually describe a process in the real world that can occur with some theory of quantum gravity. What has kind of happened is people are pursuing things that are mathematically tractable, where it's not exactly clear if it relates exactly to the real world, but the hope is that, it's kind of like studying toy models. So you introduce something that's a little simpler, and you can understand that. If you can understand that, then maybe you can level up in the future and then get back to reality, so to speak.
So go down the rabbit hole, right?
Yeah, and I mean that's it. The real challenge is even finding experiments that probe quantum gravity, because you could try to pursue one theory or another, but at the end of the day, if you don't have an experiment that can determine which theory is right, it's really just what's your favorite Pokemon card? It's like, I like Charizard. I like, you can make up all these philosophical opinions on what you think should be the right theory, but at the end of the day, the whole point of physics is to predict things in the real world. And so there's theoretical challenges, but also experimental challenges. And
most of these things have to happen in space, though, right? Like we have to go to, do we have to observe things in space happening in order to what, like gravitons and all these crazy things are?
Conventionally, you would think, right? Because gravity relates to the planets and the stars. So you would think, if I probe quantum gravity, then I must have to do something in space. But actually, even Seth Putterman at UCLA claimed that he knew how to do an experiment that would probe quantum gravity on the tabletop level. It wasn't with duct tape. Yeah, right. Like graphene or something.
Yeah.
Oh, they use Scotch tape, I guess.
Scotch tape, where they created radiation from Scotch tape. That's a funny one. But go on,
But I mean, he was claiming to have a tabletop experiment that would be able to probe quantum gravity, but he said, I don't want to do it. I would get a Nobel Prize for doing it, but I'm not going to do it because it's too controversial. And it's like, okay, yeah, maybe. I don't know. So, yeah, and okay, so the next question was about gravitons. Well, in my view, I look at all of these theories as being field theories. So when you do this, you have this inherent particle wave duality, you could say. So just as you have electromagnetic waves that relate to the photon, it's all described by the same electromagnetic field. So I actually learned quantum mechanics. My teacher in undergraduate told me that these quanta are neither particle nor waves. They exhibit particle-like behaviors or wave-like behaviors at certain times, which is a subtle perspective to take, because a lot of people just say, oh, it's a particle sometimes, and then it switches to a wave. And it's like, well, no, it's actually just a quantum field that can exhibit wave-like and particle-like behavior. And so when you take that perspective with gravity, you necessarily are forced to believe that gravitons are real in the same sense that gravitational waves are real, which have been experimentally measured. And
where have they
actually
measured the gravitational waves? Sorry, I know that's I think that's a question one of the kids asked too. Is that the thing deep down inside the Earth that they have?
Well, that one's probably for neutrinos, but they have these. Well, yeah, they do make them underground. That's true. So
Right.
it's called LIGO. So they
Okay.
have these interferometers where they basically send light down two paths. And
Okay.
it bounces off these mirrors.
Yeah.
And it's really remarkable because the mirrors, they have to get extremely sensitive, or the position measurement devices at the end of the day,
Yeah.
have to get extremely sensitive down to 10 to the minus 18 meters, which is
wow.
extremely small.
Wow, that's such a
So they need
small
the most
scale.
sensitive. Yes. So what they actually do is they have these detectors. It bounces off the end, it hits mirrors and comes back, and they look at the interference pattern in the light to try to identify if there's a shift, right? Because if you send, they're both traveling at the speed of light, they bounce off the walls, and if you make the lengths of the two arms exactly the right same length, they should come back at exactly the same time and be in phase.
Gotcha.
But if you had a certain polarization of gravitational waves that came through, then space-time would get warped.
Okay.
You would get one of the laser beams to come back, quicker than the other, and you could see a little delay. But they're so sensitive that even if you have an earthquake or even just a car driving by nearby in the facility or a little wind or something, it could cause a slight fluctuation. So then what they do to take it to the next level, they build two of these devices.
Yes.
And they place them across the world. There's one I think in Washington State. The other,
I see this one. There's this picture of this
somewhere.
massive thing or something. I don't know. This looks like it's in the middle of the desert or something. And it's 4 kilometers long on each arm. That's crazy.
Exactly. So it's best to have it in an isolated area if possible to reduce noise. But even so, what they do is they use two detectors that are far apart, and they do this for two reasons. That way, if they collect a signal, they can look at both experiments, and then if they only see it in one experiment, then it's probably more likely to due to some,
because these gravitational waves are huge, right? I mean, we're talking like the size of planets and stuff, so it should be able to detect it on both ends of the Earth.
Well, yeah. I mean, the idea is that gravitational waves are coming in. I mean, it's kind of, think of a light bulb, right? I mean, it depends what you mean by are they huge, right? So on the one hand, the waves will have some frequency or some wavelength. On the other hand, like you could imagine light having a short wavelength, but if it's diffuse enough and you have a light bulb, the light is going to spread out. And so if you have some astrophysical source, let's say you had two black holes that collided and enter a merger, they're going to just similar to a light bulb, they're going to just create this explosion of gravitational waves coming out. And so all of those waves, it will be big in that sense, and you will be able to detect it across the globe everywhere. And so, that's kind of how and the other thing they can do is they can triangulate the signal when what they do is they assume that these waves are traveling at the speed of light.
Okay.
And they use that assumption to determine where it came from, actually. So they can triangulate where it came from, so then they can talk to maybe some astronomers, and I don't know if they could figure out, hey, maybe there was something coming from
was
that
there a
direction.
black hole that happened here, right? That collided with another one.
I mean, maybe you couldn't see it, but that's something that could be done as well. So so that's kind of how it works. And so the reason I mentioned this is because that's the gravitational wave detectors that we are using, and my PhD thesis project was actually looking at how to compute gravitational radiation, and I employed Feynman diagrams with gravitons to do so. And it wasn't even quantum gravity. It was actually just classical gravity, but I was able to even use graviton scattering to figure out how gravitational waves work. So from my perspective,
these are Feynman diagrams for the kids that don't know.
So these are just these cute diagrams that help you figure out all the different
I
types
still
of
don't know how to read these things. Like going through physics, like I don't know how to read these things. But they look cool.
Yeah, it's quantum field theory. You learn it in quantum field theory, which is it's a graduate class, and a plasma physicist typically isn't going to
we don't
that,
do this.
That's dope.
It's
dope for you.
So it's mainly particle physics, but particle physics is kind of dying. They'll call it high energy theory, and now string theory is kind of taking over because really we're running out of experiments to do. So my PhD advisor, his whole
Oh, thanks for this.
The vision was basically to take the methods from the Large Hadron Collider, which is colliding protons.
Yep.
And he realized that those theoretical methods could be applied to LIGO because at the end of the day, if you're colliding protons or you're colliding black holes or colliding stars, it's still a collision process. So a lot of the mathematical tools can be carried over. So he's kind of taking tools from this dying field and applying it to this new emerging industry, so to speak, with the gravitational wave detectors, because it was actually surprising that they detected these. They were a little shocked because there was this really big black hole merger that occurred. And so but it's still it's a difficult experiment to do. It costs a lot of money.
This is the one I always hear people talking about, like, oh, they're going to destroy the Earth because they're going to create a black hole with the LHC or something. I'm just like, what?
No,
right? No.
I don't.
We're all safe, dude.
I mean, even Stephen Hawking kind of thought maybe it could do that, but I don't really see how.
This thing is huge. Have you been to LHC? Have you been to CERN?
No, I haven't. So
yeah, this thing looks cool.
But it's pretty cool. They have all these really huge magnets to get these particles. They have to get a really fine beam of particles and they spin it around. And so yeah, I mean that it's this type of thing where these experiments are getting so big that they're really built to detect the things that everyone is very confident that are there. So it's a little bittersweet because we're putting all this money to essentially test these things that everyone assumes must exist anyways. And with the LHC, it's really interesting because you can't just, the data is so complex. You can't just look at the data and figure out what happened. You have to have a theory and see if the theory matches the data. So that's another challenge with that experiment. It is the data itself is so complex that it's different than most other experiments where you can just do the experiment and interpret the data very easily. So
this looks like a mess trying to like analyze this, dude. Like I'd be like, what? Excuse me?
Exactly.
Right.
So
like, what are we even looking at here? What's going on here? Is this just you're just reading a bunch of EMR radiation being detected or something? Like what even is this?
Right, and I mean obviously that's some image generated from a bunch of data to look cool. So I mean, presumably those colors represent different things. Maybe
trajectories
one could be for photons, trajectories of particles. Maybe some are electrons. It depends on whoever made that figure. Yeah. They used to have these bubble diagrams that in the old school experiments that track out the path of the particles, but
yes, I know what you're talking about.
Complex sensors.
What were they called?
Bubble chambers, I should have said.
Bubble chambers. Yeah. This is the old school way of detecting things, right? With the PMTs, photomultiplier tubes, right? This was the old way we used to detect like quantum things going on. Was this? Yeah.
Oh, so what was the third question? Let
me go back to what it was.
Let's see.
So Marcus said, thoughts on the graviton in general. Is researching quantum physics a job that's profitable enough to live a decent life? Yeah, that's a good one.
Quantum physics, yes, because you can get into industry. So condensed matter physics is really the most popular area of physics now. So it's kind of strange because at the kind of mainstream level, maybe people talk about unification and string theory and people say like physics is doomed, but really physics is not doomed whatsoever, theory or experiment, because if you look at the papers, the journals, the conferences, condensed matter is dominating everything right now, which is not what I studied actually. So if you get into condensed matter theory, even it's still highly theoretical, but you're looking into the quantum properties of matter, which is useful for industry. So
this is for quantum computing, right? Quantum computing is where this is all going.
Quantum computing is one direction, but even things like spintronics or just trying to make even better classical computers or just making new chips, before even, quantum computing has obviously been a hyped buzzword, for good reason, because it will revolutionize things once they figure out how to get rid of all the errors and get a cleaner signal overall. But yeah, I mean, quantum computing isn't quite there yet, but if you're younger, that is a good thing to get into because
it will get there eventually.
Exactly. You can kind of get in on the ground level where, people understand how it works theoretically, but no one really has a truly amazing quantum computer. I mean, there are certainly cool experiments that have been done with quantum computers at this point, so it is something that is real, but it's not like it's revolutionized our lives yet, like it could. So if you're a little younger out there and you got into quantum computing now, it could be really exciting because you could kind of get in at the ground level where you could actually be a part of that whole movement and maybe find some important discovery. And then, that's a great way. So certainly with quantum physics, there's applications there. Now with quantum gravity, it's very difficult to get a job related to quantum gravity because
it's so specific, it's niche, and it doesn't really have much application right now, right? Yeah. We need money.
My PhD advisor was passionate about quantum gravity. That was his main interest. And even as a tenured professor, he still felt that he couldn't just study quantum gravity. So what he did is he studied processes at the LHC. And that was his way to make money, is to, do work that are related to the experiments. But, at nighttime, let's say, he really wanted to work on quantum gravity. So what he did is, this is
got something to pay the bills.
Tip. It's like you kind of need to have your personal track of what you, unless you're Nickelback and you just happen to make music that everyone loves.
Everybody loves Nickelback.
Awesome. It's not like they're trying to sell out. They just honestly just write the music that they like, and it just so happens that people like it. Most people, especially with science, it doesn't always work out that way. Your interests aren't necessarily aligned with the public's interests, which is totally reasonable. So it does help to try to identify what the public cares about and try to figure out, are there analogies or is there a way to kind of bridge the information? So that's what his name is Zvi Bern. What he does is he figured out this method that figured out how to take solutions from QCD and gluon scattering, which is useful for the LHC, and he figured out how to make this thing called the double copy, which transforms those solutions into gravitational solutions.
Okay.
And so he was motivated to study quantum field theory related to these experiments and apply it to gravity, and he found this transformation.
I see. It was. He's got a wiki page for it, dude. Double copy theory is a theory that was. Oh wow, this is very cool. I didn't know this was his.
Yeah. So that's Zvi Bern. He came up with that, and so he has basically all of the records for perturbative quantum gravity scattering. So graviton scattering. So a little history lesson. Basically, you hear that quantum gravity has problems when you try to quantize it. You run into these infinity problems.
Okay.
The way it's typically described is you calculate the probability of a certain process occurring, and the probability is infinite. You do the calculation, and all you get is infinity.
But you need it to be 1.
They're supposed to be, in between 0 and 1. So
it's got out of. You can't have an infinite probability.
Getting a probability of 5 would kind of be a problem, right? But getting infinity is a serious problem. So that's essentially what happens. But it actually turns out that they say that at one loop, which is the first quantum correction, so they do this, it's like a Taylor series expansion. So you kind of have a constant, then you have a linear term, then you have a quadratic
This is cool,
term.
because we were doing, remember someone was asking about like Taylor series and Fourier transforms. Yeah, okay. So this is like approximations, I guess, yeah?
It's exactly that. So they say that you can take h bar, which is Planck's constant, and the classical limit is sending h bar to 0. So
oh wow.
Maybe you guys know, right? If you do a Taylor expansion about a small parameter, right, the lower order terms become more important. So you can kind of neglect the higher order terms and just focus on the lower order terms and get a good approximation. So that's the same exact thing. It's really just a Taylor expansion. So we do that with quantum field theory as well. And you get these perturbative quantum corrections. And so they would say that gravity is miraculously finite at the first quantum correction.
Okay.
But then it diverges. It runs into an infinity problem at the second quantum correction. And that was figured out in the 1960s. That the one loop solution, they call it the first, because you have these Feynman diagrams with loops, and the loops count how many factors of h bar you get, basically.
Okay.
So that was a hint right there. The fact that you were able to get a finite solution at the first quantum correction, so it does sort of work a little bit, but they couldn't figure out the higher order terms. And so another thing that my advisor had solved was solving the 2-loop graviton problem. It turns out there's this way where you add this term in the general relativity that doesn't change the classical theory whatsoever. and it fixes up the quantum mechanical properties, and he was able to explicitly compute it at the second quantum correction, which to me is just a mind-blowing and amazing result, because it's hinting at this idea that maybe quantum gravity actually works.
Yeah.
Because it's at this point where the string theorists, their whole point is, well, quantum field theory doesn't work, so let's move on. And loop quantum gravity as well, that there's all these people.
You got all these camps, and they're all like fighting with each other, you know, and they're all trying to like get any sort of like minuscule funding that's out there in order to like prove their theory is like correct.
Yeah. And it was strange because the way he wrote the paper, when I read the paper, I couldn't even tell that he did what he did. He was so careful and conservative with how he worded it, because he didn't want to get too much backlash.
Yeah.
No one in the community even understands it. The only reason I understood that he solved it was because he was my advisor, and I heard him talking to collaborators.
He's like, ooh, keep it secret.
And it wasn't even that. He was just like a really nice guy, and just didn't want to
didn't want to ruffle the feathers.
Yeah, exactly. Like,
but you got to break a couple dishes in order to like dance, you know.
Well, the problem was he said for his double copy, he said that he showed how there's the solutions of QCD, the strong force, which is what holds atoms together, or the nuclei together. He showed how those solutions relate to gravity. So he in a popular article, it was written up where maybe he was quoted, and he said, "Oh, maybe this will be inspirational for unification." And he got a lot of hate mail. All the physicists, you know, it's kind of like Lord of the Rings. Everyone's like, "My precious,"
my precious.
So it gets a little heated sometimes. So he got a lot of flack. He got a lot of pressure just for even saying that maybe his work will be influential for something in the future. Everyone was like, "Oh, you can't say that." So ever since then, he's been a lot more cautious,
like a meek.
About
He's
his
just like,
claims.
oh man.
So he's just focused on, and that's just his personality as well. When he goes to conferences, he's not super talkative, but it's like he gets the results, he does the math, and he finds the solutions. And you know that it's money talks. I mean, here I guess computation talks, so to speak.
Yes, computation does. One of the students was asking about Planck's constant. They said, like, what is Planck length, or like where does it come from? I say it's like the refresh rate of the universe.
Well, yeah, I guess that would more be like a time or frequency. But yeah, so it started by looking into thermodynamics and black body radiation.
Okay.
And eventually they figured out there's this constant. And so really thermodynamics led to this discovery of quantum mechanics. And after a while, they realized that there's this way where you can set up these things called natural units.
Okay.
Where if you think about it, we always have to measure things with dimensions. And
like inches or feet or something, right? Yeah.
And maybe you guys have done some physics homework in high school, and you got -5 points because you forgot to put the units. You just put the number, and you say, "Hey, but I got the right answer."
I got the right answer. Whatever,
dude. Didn't write the units.
Yeah, no.
Right? Is it meters or is it centimeters?
Yeah.
So, but it turns out, I mean, at the end of the day, all these units are kind of man-made. So to speak,
they're arbitrary.
Like
they're human constructs.
What should be a meter stick? Exactly.
Right.
They figured out, the theoretical physicists basically realized there's this way where you look at these different constants. There's h bar, which is kind of the quantum mechanical one. Then there's the speed of light, which we'll call c. That relates to relativity. And then there's g, big G, which is Newton's gravitational constant.
That's the 9.81, right? Or are we talking about the 6.62 10 to the -34 one?
-11, I think. 10 to the minus.
Oh, -11, maybe.
Yeah,
no, it's been a while since we've done homework.
-34, that's the Planck length probably.
Yeah,
So yeah, you have this G, C, and H bar, and it's kind of cool because these are associated with different theories. Once again, gravity, quantum mechanics, and special relativity, relativistic processes. So you can kind of take these limits of these things going to zero. Like if you imagine you have things that are a very slow velocity in comparison to the speed of light, then it comes non-relativistic. If you have other processes where h bar doesn't matter, then you can go back to the classical limit. And so when you combine these three units together, you can kind of get dimensions of any other quantity because they have dimensions themselves. So you can isolate a length that is made out of G, H bar, and C. You can isolate a time. You can isolate a frequency. You can isolate a force.
Oh, very cool.
Any unit you can think of.
And it's like the smallest thing you can have. It's like the smallest.
Well, it depends on which quantity, right? But here's the interesting thing. So when you have all three together, it's a good hint that you're studying quantum gravity because you have this big G and you have H bar.
Uh-huh.
So people started thinking about, well, what if you had black holes in quantum field theory? What would that mean? And this is where it gets interesting. You think about doing a measurement. You're trying to measure something. Like we have electron microscopes. So what they do, it's really just a scattering problem. You take electrons and you fire the electrons at this object.
Yeah.
And the electrons bounce off, and then you collect the electrons, and you reconstruct an image based on how things scattered off the object.
Okay.
And so you can theoretically now imagine, well, what do you need to do to measure to a smaller and a smaller and smaller scale?
Something smaller than an electron, right? How can you measure something smaller than the thing you're bouncing it off, right?
Yeah, so that's another problem, right? But in general, you can get to smaller lengths by going to higher energies.
Oh, okay.
So there's this common theme of when you put things in natural units, you can they'll often call it mass units.
Okay.
And mass E equals mc squared. And so with these natural units, you can set everything to one. Well, not everything, but you set G, H bar, and C to 1. And
Oh, yeah,
cool
dude. Setting everything to 1, dude.
It trips people out, but
It does,
what
yeah.
you can do is if you're smart, if you know you have a force and it's in natural units and you put all those constants to 1,
Mm-hmm.
you can reconstruct the units by just understanding the dimensions because you can get to any units with these natural units. And so that's one little trick you can do. So when you're doing theory calculations, it gets annoying to keep writing down the H bar, writing down the C.
Yeah.
the
You're
4,
just like,
C,
why do
the-
I keep writing it? Just
you
set it equal to 1.
Don't write it.
Yeah.
Just set it to 1, and once you get your answer, if you need to use it for an experiment, you can actually figure out how to reconstruct it. So that's why it's totally kosher to do. You can always figure out how to put, assuming you learn how to do it. You know, other people, they're kind of weirded out, and they're like, hey, I feel like you're cheating when you set it to 1. It's like,
Yeah,
no,
I don't like that.
it's just a math trick. But getting back to doing measurements,
Yeah.
if you go to higher energy, you can get a smaller resolution.
Okay.
But we also know that you can eventually form black holes. So
Oh, what?
happens is if you get enough energy in a small space, in a small volume, that energy will collapse into a black hole.
Oh, man.
So the Planck length is really the limit of how small we currently can measure things based on our understanding of how measurement devices work, because you could push things to higher and higher energy to get that smaller resolution. But now you're getting such a small resolution and you've increased the energy. It's like a doubling effect where you get small and high energy. So it makes it easier and easier. Eventually, once you get down to lower than a Planck length, you create a black hole and you lost the energy. The electron
there's
goes
no
into the
information
black
anymore.
hole,
It's not coming
you don't
back.
get the information back. And so the measurement process just got destroyed. So
Oh, no.
that's why they say, I mean, at the end of the day, we don't know. Is space-time quantized? Is it discrete? We don't know. All we know for sure is we can't measure things on a smaller scale.
Oh, that's very
So
cool.
that's where the Planck length comes in. It's basically the smallest measurement that you can measure. And then so once people realize that, they start, and it works for time as well. So
Right, yeah, there's a minimum time
you can't measure
frequency.
something in a small enough time. You can't do smaller than that. And then people kind of conjecture, well, there's this Planck mass, but it's kind of inverted, as I was saying. So now the Planck mass, it's weird. If you look at the Planck mass, it's not that big, but in comparison to the mass of the fundamental or elementary particles, it is a pretty big mass. I mean, it's, the mass
10
of
to
a
the minus
table,
8
the mass
kilograms. That's not too bad.
it's
10 to the
tiny.
minus 8.
It's tiny.
It's not
So,
that bad.
yeah, I mean, some people see that and are like, oh, it's a small mass. So, maybe I can't have a smaller mass than that. No, but look into the mass of the electron.
Yeah.
The mass of the electron is much smaller. So some people
That's the
say
minus
that,
34. I think the mass of the electron is minus 34.
Well, it depends on your units.
The kilograms one, I think. Yeah. Oh, minus 31. My bad. But yeah, that's less than a Planck mass. Yeah.
Yeah. So the idea is people are saying, once again, I was saying energy is inverse to length. So if there's the smallest length scale, it might almost imply a biggest energy scale.
Okay.
And we also know that E equals mc squared, and we just set C equals to 1, so we can even go bolder and say E equals m.
Oh,
right?
no.
And so now you say mass is energy, and so if there was an energy limit, now it's a mass limit. So some people say all of the elementary particles should have a mass that's less than the Planck mass. So it's a little counterintuitive, even though it's a Planck scale, a Planck quantity. The Planck mass is kind of the upper limit for these elementary particles, is what people have suggested.
That's cool. It's like the limits on
So
things.
yeah, that's all the Planck units, Planck scale.
Plonky stuff.
There we go.
That's cool. All right, let's move to the next question. We got a lot of questions today. I love this. This is great.
It's good. I love it. This is fun.
All right. Saint says, what is the best advice you have for an upcoming person who wants to get into physics in college? What does it take to be a scientist? Hardest obstacles? And did you ever have any thoughts of wanting to do anything else? And he's an up-and-coming senior. Do you have any advice or tips for me on how to be successful in physics? Yeah. It's a lot
I would
there.
say overall, just starting with success, it was weird. I thought of this when I learned calculus. It somehow clicked in my head where I realized I think it's important to set ambitious long-term goals
Okay.
and set realistic and achievable short-term goals.
Mm-hmm.
So you can have this vision, like dream for the stars for the long term.
Yeah.
But then when you're waking up in the morning and it's like, what am I going to do today?
I still got to make my bed.
Don't try to, yeah, just, or even just try to do something you know you can achieve, and set the bar low, but actually get it done.
Yeah.
And what it kind of trains you to do is the idea is you want to stack these small things into a big thing.
Yeah.
And so I kind of, I don't know, for some reason, whatever reason, thinking about infinitesimals kind of made me think, oh, like small change on a small scale, do something, you don't need to do something big today. Just keep your head down, keep learning one step at a time, right? Maybe you're not learning quantum field theory yet. Maybe you think classical mechanics is boring.
Yeah.
But the honest truth is if you just take that little step and take in that one piece of information and you master it, you're going to get better at mastering things in general. And as you get to more complicated things, you'll kind of ride with that. So that's a pretty general recommendation overall, not even related to physics. And then with physics overall, I mean, right, with physics, it's not really about memorizing stuff. I would say it's about training your intuition. And I really thought about it as when I learn physics, when I truly learn it, it actually makes me a better person. Like it makes me, I look at it as training my own intuition about how to understand and see the world. So, and really it's also just about problem solving.
Yeah, it's a way of solving problems.
Honing your skills. It puts you in a certain mindset to get you good at solving problems. So I think the cool thing about physics is that it's very it's hard to see the connection sometimes. It's a little abstract, but once you get good at physics, you get good at solving problems in general. Yeah. But there's also a potential trap because it's hard sometimes if you go into physics. I mean, depending on what you do, obviously there are ways to get into industry. There are certainly a lot of opportunities to do that. But if you get too theoretical, kind of your only option is to become a professor for the most part.
Yeah, right. Yeah.
And it's pretty competitive. Like
that's a crapshoot. That's very hard.
It's very hard. It was described to me as almost like getting into the NBA, where you could be really good, but every
stars have to align.
It's getting weeded out, and it's a little unfortunate because I feel like a lot of people that go into graduate school, it's almost like they don't know what they want to do as a job, but they're good at school, right?
Yeah,
and
I'm
they
good at
don't
school.
really know what they want to do, but they're good at school. So I'll just keep staying in school.
Yeah, stay in college forever, dude. Avoid the responsibilities of having to live your life, dude. Just keep learning things.
Yeah, obviously it's great to learn things, but it is also like it's kind of if you don't think about what you want to do, if you don't find a path in the industry, like it can get kind of sad for some people where maybe they just didn't understand that politics matters in every life. So
I thought there weren't any politics, but there's so much in academia. Right. It's nuts.
You would think that, and it's strange because scientists, they really don't care about politics and the politics of, overall academia is a little democratic, let's say.
Yeah, a little liberal.
More democratic than, more liberal than Republican, but still, you'll see these professors kind of almost mock politicians, and it gives you this idea that, oh, science has no politics. They don't care about politics, but no. At the end of the day, politics is everywhere. It's still humans interacting, and there's always this culture. So you're going to go work for someone. I mean, I would recommend just be extremely respectful to the people that are older than you, the professors, and realize when you go to a university, you have this golden opportunity to pick the brain of some of the smartest people in the world, right? Like you use that to your advantage. It gets really, it's kind of strange. After you leave, they won't respond to you.
Yeah,
you know?
they're just like, no.
Like,
Like, I don't
email. You can email professors. I mean, they get all these crazy emails from all these people. Read my paper. Blah blah blah.
Yeah.
Right? They're so busy that they don't respond to any emails. So it's really a blessing when you're in college. You get access to these professors who are willing to teach you, and so use that to your advantage. Ask questions. Pick their brain. I always did. I mean, there's kind of two types of students: the kids that sit in the front of the class, kids that sit in the back. And it's actually kind of people say it's better to sit in the back because then you're taking it all in. But I was the one that would sit in the front. I would ask all the annoying questions. It has its pros and the cons because on the one hand, if you ask too many questions, you'll eventually ask a dumb question. You'll look like an idiot. But on the other hand, if you have a question and you don't ask it, you're not going to get the answer. So
right, yeah.
You know, I at the end of the day, I think it's about a balance with everything. You want to find the balance. And just really try to have respect for these people, but also, you know, take advantage of that opportunity to ask them questions, get to know them.
Yeah, they're going to respond to you.
Learn from them because that's the only time you have to learn from them. Another tip of advice is I would say, try to perfect it, get as good as you can at what you're doing. Like, let's say you want to go into physics and you get there and you're thinking, oh, I'm gonna go to graduate school and I'm learning quantum mechanics now as a junior in college. Let's say I'm gonna take graduate quantum again. So I don't really need to try that hard because if I don't really understand everything, I can figure out again in grad school. But that doesn't really work because they're gonna make it harder, and you really do need to get grounded in those fundamentals and to build on that. So really just try to perfect as much as you can. Just that's what I'd suggest to do. You know, do your homework.
Do your homework, kids.
Try to understand.
Go to office hours.
Don't just try to do your homework and be like, okay, I finished that problem. Try to predict what are all the possible problems that could be asked of me. And understand how this problem fits into that context. And that's really the point of physics. It's not like organic chemistry where you're just trying to memorize
this reaction or memorize
formulas.
this
You're trying to learn the intuition for how to solve these problems in general, right? And you know, as we get into AI, people are talking about general intelligence. Think of it that way. Try to build your own general intelligence. Don't just solve the problem and just spend a couple minutes, be like, okay, what could have they changed?
What could they have changed?
Harder. How could they make it easier? What if they gave me these variables instead of those? How much information do I even need to solve a problem? Just try to understand that. And I think that's a real key for kind of going from homework to tests, right? Because some professors, they'll get lazy and they just
put the homework questions on the test. Yeah.
Others, they'll purposely set it up where they try to trick you, where they purposely orchestrate their homework, where they put it in one direction and then they just do all this wizardry to give you this problem, and you're like, what? I've never seen this before.
Yeah.
Secretly, what they've done is the concepts. You should have been able to abstract the concepts.
Instead of memorizing an equation, you should understand why the equation works. And so if they switch up a variable, you know how to do it.
Can you derive the equation, right? That's even better, right? So, you know, are you just memorizing the equations, or are you understanding why the equations work at some level? Try to get to that level. That's what I recommend. Let's see, what other...
I think it was good.
What are the hardest obstacles? Yeah, I mean, and to my surprise, in graduate school, I thought it would be the science, the difficulty of the material of doing research. For me, honestly, personally, it was just the politics. Really getting through the political landscape. I almost I kind of shot myself in the foot. I was willing to do controversial things. I was willing, at the end of the day, I didn't want to just become a professor for professor's sake. I only wanted to be a physicist if I felt like I could actually help the world with my contributions. And that was just me. I mean, other people, they like physics, but they don't really care that much. They're just there at that point, and they're like, what do I need to do to become a professor? That's all they wanted. And for me, I didn't really care. Almost if I became a professor and then I just didn't know what to do, that was almost the worst case scenario for me. So that I didn't really worry about the politics, and I tried to test
just wanted to focus on the
grad
science.
school.
Yeah, you just want to work on the science. That's what we're there for.
I purposefully would do two crazy things just to see. I treated UCLA as a test case for the real world, and I wanted to stress test UCLA to see like what I could get away with.
Yeah.
But the problem with that is I didn't realize that, oh, I need to get these professors to actually like me. I mean, when I was in the classes, you know, I could get professors to like me because I would ask good questions. I would be engaged. But eventually I would I would ask the difficult questions. Like, it was almost like I started to figure out how to push people's buttons. And, you know, they don't like that. You know, show them respect. Like, even if you understand something that they don't, you know, just don't talk about it.
But like, if they're wrong, I feel like you should be able to provoke them and be like, "Hey, I gotta rattle the bush." You know, like, this is wrong.
Yeah, but how is that going to make them feel as a human being, right?
Right.
They're not going to want to interact with you after that. So
yeah.
And it was surprising. I mean, I knew that academia was kind of reserved, and I knew what I was doing, but it ended up being a lot worse than I thought it was in that sense, where there was a lot of backlash there. I just had to go through some personal stuff, so that was probably the biggest challenge for me.
Nice. All right, awesome. Good questions. Let's move on to the next one. Let's see what we got. Destiny Cove, where do the charge in things like haptons and leptons come from, and why do certain equations before quantum corrections go to infinity? And have you ever met Michio Kaku?
All right, cool questions. Yeah, so obviously that was just a typo at the keyboard. So there's hadrons and leptons.
Hadrons and leptons, yeah.
Yeah, so leptons are basically things that have electric charge but no color charge. So just a crash course, there's the standard model of particle physics, and because he's asking about, or he or she is asking about charges.
Yeah.
And so we all are more familiar with electric charges, right? But when you get into the standard model, there are these other exotic charges. And it's really a difficult question to answer. Why are there these charges? But what we know for sure is, at least as far as our experiments can tell, these charges do exist. So there's this weak force, and then there's this strong force. And so the weak force has its own associated charges associated with it, and then the strong force has its charges, and they're kind of generalizations, more complicated versions of electromagnetism. So the strong force, they call it color charge, and they just came up with this cool acronym where it's described by this Lie group called SU3. There's a 3 in it, and so you know how you have RGB.
Yeah.
And it mixes to get white light. So they kind of ran with that analogy, and so they said there's 3 different color charges. So it's not literally like electromagnetism. You have 3 separate charges. There's a red charge, green charge, and a blue charge. And these quarks are what make up the hadrons. And so the hadrons are defined to have color charge, and the leptons are just those particles defined to not have color charge, basically. And then, you know, there's also this weak charge. And so basically what they've realized is you go into atoms and there's the electrons floating around. Then they found the protons and the neutrons, but it turns out that these protons and the neutrons are composite particles. So they're hadrons, and they're comprised of 3 quarks. And for whatever reason, when you work out the mathematics, this strong force is a very strong force, as it turns out, which is why
that's why it's called the strong force.
Believe it or not. And so they like to form these triplets.
Yes.
Because when you put the R, G, and B together, it's white. It becomes stable.
Okay.
And so the gluon is the force carrier of QCD, the strong force.
Okay.
And so the gluon is kind of like the generalization of the photon or electromagnetic forces, electromagnetic waves. So these gluons are the force carrier that's binding these quarks together into the hadrons. And they did these experiments called deep inelastic scattering, where they just collide particles essentially, and they could eventually get into the structure, and they realized that there's solid evidence that these protons and neutrons have substructure of these 3 quarks.
So we've proven that there are subatomic particles? Like, we know for sure? It's not just like some weird theory we came up with?
Yeah.
Oh,
yeah, it's not. There's
that.
a lot of hard experimental evidence suggesting it. I mean, you could get into debates about how direct the evidence is, but it's pretty direct. I mean, we do know that through this deep and elastic scattering that there's objects, like you see 3 separate objects. I mean, it's really complicated to get into that, but Yeah. So there is definitely this structure there, and in terms of all of the different types of particles that we find in nature, there's there's baryons and mesons. So the baryons have 3 different quarks, and then the mesons have it's a quark antiquark pair.
Mm-hmm.
So it's like 2 quarks, but one of the quarks is an antiparticle. And so there was this zoo of particles that they were finding in these particle colliders. And when you study this standard model of particle physics that introduces the strong force and the weak force, the electroweak force, it once you understand what these elementary particles are, you can put them together like building blocks, and it exactly matches the particle spectra that we see in nature. So that's, I mean, it's somewhat indirect evidence, but that's really strong evidence that we understand what the blocks are. It's like almost like Lego pieces.
Yeah, it's Lego pieces. I'm about to say it's like Legos.
In certain ways, and then we put together it's like we make all the Lego piece, things possible.
Yeah.
And we see those things in nature too. So that's a really good match. And also just the explicit calculations of how these things interact. There's discrepancies here and there, but it's a pretty good match overall. It's with how difficult it is to do these experiments, to collect the data. It is really impressive with how good they have been able to match the theory with experiment. There's obviously errors. Not everything is perfect, but yeah. So I don't think we really know why these charges exist. I mean, you could
that's a big question, like why?
That they come from some grand unified theory, but then you just have the same question: why did that grand unified theory that has even more complicated charges? Why those charges, right? So it's kind of like a little kid asking why. Why this? The mom gives an answer. You can just keep asking why. So really, with science, it's more about how a lot of times than why.
Why? Yeah, it's like how does
why
this
is
happen?
a hard question to answer.
Yeah. I think Jamarcus says,
Let's
isn't
see,
there something where there are?
Oh yeah.
Yeah.
I gotta slip in a little thing for
do it.
Kaku as well.
Yeah,
so
yeah,
I've
do it.
never met him, but he did actually goes on a news channel, and he talked about a paper that I was a co-author of.
Ooh.
So that's the coolest thing.
You've gotten a shout out from Michio Kaku?
He went on the news and he kind of was like, "Oh, that paper's like something. It's cool to talk about at dinner parties, but whatever. But I'll take it." It was about this self-simulation hypothesis, and then I don't know. I guess someone in the public saw it and was like, "Oh, Michio Kaku, what do you think about this?" So but he said some quantum physicists are thinking about this. So yeah, he called me.
That's cool. He called you a quantum physicist.
That's dope.
Wow, that's super cool. I think Jamarcus was asking, says, isn't there something where there are a bunch of other quarks and particles that fluctuate in and out of quantum fields or something? Oh, I don't know what that means.
Oh yeah, so it's really confusing. If you look at it right, it's not that bad, but the particles that we see in nature, they're physical particles, they call them, or they also call them on-shell. That's the technical term. They have these physical particles, and when you study it, it turns out, I mean, this is one of the most mind-blowing discoveries. I mean, it's not that I discovered, and this is just when you study physics. When you put a charge, an electron, in the vacuum, you get all these virtual particles. It polarizes the vacuum. So and these virtual particles, they're inherently quantum mechanical in nature. They cannot be measured. By definition, they are not classical. They're off-shell. They're virtual particles, and they're fluctuating in and out of the quantum vacuum. They're extremely short-lived, and you literally cannot measure them. But they are used in all of the computations when you do this quantum field theory business. So when you're colliding these protons and you're calculating how to get these interactions, you need to have these virtual particles. And the virtual particles are what runs in the loops of the Feynman diagrams.
Okay.
And so they always get emitted and absorbed by interactions, so like you can't really measure them. And so I mean that sort of gives some information about what they are, and they are mysterious. It's very strange because it's until you study those objects, there's nothing else like it, because it's something that we think should exist, but we by definition can't even measure it. So it's an indirect thing.
Yeah,
we can infer what would occur if they're there. And we see that. And the thing is, when you remove them, you only get classical physics. So these virtual particles are required for those quantum corrections, loop by loop. In that perturbative expansion in that Taylor series, every time you go to the second Taylor expansion level, at the quadratic level, you have 2 loops, and you have 2 virtual particles running in the loop. So if you have no loops, then there would be no virtual particles, and then you have no quantum mechanics.
And everything just breaks down.
They're really essential to quantum theory.
Oh, wow. That's cool. Nice. Destiny also had a little side question. He says, how does string theory create 10 dimensions? I know M theory adds another to create 11, and that time is supposed to be the 4th dimension. But, like, yeah, where do these 5, 10, 12 dimensions? I think you've talked about it before with me, but yeah.
Yeah, so at the end of the day, they get into these things called quantum anomalies. It's a very technical and difficult issue. It's even really amazing physicists who are extremely smart have made a lot of errors with this quantum anomaly business. But essentially, there are these issues in these quantum field theories that people think they're issues, and string theory proposed a solution to these anomalies. And it turns out that you can kind of study things in arbitrary dimensions sometimes. And so they kind of did this. And so when they did the calculations to remove these anomalies, it only can occur in certain dimensions.
Okay.
And so if you
Which we're used to 3 dimensions, right? We're just used to 3D world is like X, Y, and Z in time. But then these other dimensions are what? Like momentum or something?
Well, that's the thing. No, I mean, there isn't a consensus exactly on the understanding. I'll get to it a little bit. I'll give you my interpretation at the end. But okay, right. So obviously, we experience 3 dimensions of space: X, Y, Z. We can go forward, back, left, right, up, and down.
Yeah.
And then Einstein's relativity. That's really what introduced this concept of space-time. So we experience time. We always go forward in time. But really, a dimension is just a parameter, right? So you have a position, you have a location. But if you think about an event, right? And when you go to a party, a friend says, go to my house.
Yeah.
They give you more information. They say, go to my house at this time.
Yeah.
Right? So positions have 3 coordinates associated with them, but events have 4 numbers associated with them. So really, it's just the 4th dimension of time. It's hard. We can't visualize it. We can't see it. But I just start thinking of it as a collection of numbers.
Just information. It's just like an address.
It's just information. Or, I mean, have you ever worked with an Excel spreadsheet that has more than 4 rows in it?
Yeah.
I mean, that's all I'm talking about, really. I mean, you can get into the sophisticated notion of what it means to be a vector and talk about transformation properties. But at the end of the day, it's just a mathematical array, a collection of numbers. So that's where I get started. So then string theory comes in, and they're trying to remove these issues that are in quantum field theory, and they find a solution, but it only works in certain dimensions. And so there's 2 types. There's this bosonic string theory, and that's in 25 plus 1 dimensions. But
25?
So that doesn't have fermions. So there's bosons and fermions, and the electron and all the matter particles, for the most part, are fermions. They spin 1/2, which is another weird thing within itself.
Yeah, spin. Yeah, spin's a whole other thing.
They know that we need a theory that describes matter.
Yeah.
So that and the supersymmetry business, the SUSY or supersymmetry, is a symmetry that relates the bosons to the fermions, and the bosons are the force carriers. So and the Higgs field as well as a boson. So photons, gravitons, gravitational waves. The gluons, the strong force, the weak force, all those force carriers are bosonic in nature, and all of the matter particles like the quarks, the leptons, the neutrinos, the electrons, those are all fermions. And this supersymmetry is this type of transformation. Think of it as a type of abstract rotation where you're rotating from one type of matter particle to another type of matter particle. And that's really, if you think about 2 dimensions, like you have X and Y, all the time you make plots, and the plots you're making, it's a 2-dimensional plot, but the plots you make, it's not always of space, right? Sometimes you make a plot of voltage over time, right?
Temperature versus time, current, resistance,
Right. So it gets to a point where you can start playing games and say, well, that's a 2-dimensional plot, right?
Yeah.
And it has nothing to do with space. So really the way to think of these extra dimensions is it's providing room to describe what matter is. That's how I look at it. Because what they end up doing is, it was realized that to get rid of these anomalies, they need to go to 9 plus 1 dimensions. And so they did that. But you know what's going on? Our reality is
Yeah,
in
yeah.
3 plus 1
What?
dimensions.
Yeah, we're at 3+1.
So they started doing this thing called compactification, where
Okay.
you basically project
You
from higher
project it
dimensions
down
to
onto
lower
something.
dimensions,
Gotcha. Yeah, like a
and
shadow.
then you pretend, yeah, and then you can also shrink or compactify the extra dimensions to make them really small. So then you kind of argue, oh well, these dimensions exist, but they're so small we don't see them,
Yeah.
and they're kind of embedded in space-time everywhere. So it's like you go to a point in space-time, but you still have these extra numbers,
Yeah.
right? So just because you specify X, Y, and Z, you still have these 6 additional numbers that you can specify. And so they started trying to play with the idea, well, maybe this is related to the matter content. Another way I like to think about it, this is kind of a profound concept, which is conservation laws. So,
Okay.
and this is actually, it was
Like
a
we have
discovery
conservation
that-
of energy, we have conservation of mass, right?
Exactly. Momentum. So let's focus
Momentum.
on energy and momentum. So originally, Emmy Noether was trying to figure out the math for quantum field theory. She discovered one of the deepest principles about classical mechanics, which is that when you have a continuous symmetry, when you can infinitesimally rotate something and get the same object, like a sphere.
Okay.
If you take a sphere and you rotate a sphere, it looks the same. If the sphere is perfectly white,
Sure.
you'd rotate it and it comes back to itself. You can't tell it's different. So that's a symmetry, and it's continuous because you can infinitesimally rotate it.
Okay.
And so it turns out that whenever you have a symmetry like this, there is always a well-defined conserved quantity.
Okay.
And so we study symmetry in physics, and because of that, we find these conservation laws. So here's a couple examples. We want the laws of physics themselves to be constant over time, which is a reasonable thing. You don't.
Yeah, I don't want it to
annoying.
change. Yeah, that would suck.
Right.
We discover something and then the next day it's different. Like
It's Wednesday. Now we need a new theory, right? So
Yeah, no.
that's a symmetry. And literally because the laws of physics are constant over time, the conserved quantity is energy. And literally because we also want the same theory over space to be the same. It'd be weird if you go to one galaxy and it's just different physics, right? There
Right.
should be one theory that describes how all of the galaxies work.
right.
And so that gives another symmetry over space, which gives momentum conservation.
Ah, okay.
And if you think about it, momentum is a vector. It can you can have momentum in a certain direction,
Yes.
right? And just as space has a direction, there's a vector. So, and also it's self-consistent in the sense when you study relativity, you get into space and time get unified into a 4 vector.
Okay.
Energy and momentum get unified into an energy momentum 4 vector. So
Ah, okay.
these are conjugate variables in some sense where because you have consistency in one, you have conservation of these other. And as we were saying, there are these other charges, right? So
Right.
there's electric charge, there's color charge. All of those
Spin.
different charges have their own conserved quantities. For this story, I'm going to leave out angular momentum just because it makes it a little more difficult to talk about. But yeah, that's another conserved quantity. But the angular momentum, it's kind of combining position and momentum already.
Mm-hmm.
So, but yeah, I mean, you could get into that too, and maybe you could say that maybe there's even more extra dimensions associated with that. But if you study electric charge, it's conserved, right?
Right.
So if it's conserved, it almost implies that there's some other dimension that
Okay.
exists
Ah, okay.
that has a continuous symmetry such that you get this conserved quantity. So I like to think of the extra dimensions as really trying to unify the conservation laws of nature.
Oh, I like
where
that. That's
we're
cool.
unifying energy, momentum, and charge conservation. And that's really how I look at it. And I've put out some work that is kind of a generalization. Well, it's a simplification and a complication of string theory at the same time.
Is it on
I go into
archive?
higher dimensions.
Do we have it? Is it on
I
archive?
certainly have some papers. Yeah, you could just, I don't know, just Google David Chester Archive and then click on any paper and then click on my name and then you could see all of my papers on archive and then whatever from there.
There you are.
Yeah, that one's actually that one you clicked on.
This one right here?
Yeah, this one's, it's kind of cool. It says in the title 6 dimensions, but it actually goes into
Is that just so
16 dimensions?
Is that just so you don't step on toes? Like if you came out and you said, "Yo, 16 dimensions," they'd be like, "Nah, dog, reject him right now." You're like, "Okay, 6, but I'm gonna sneak in the 16."
It turned out that the reason why I did that was because I was trying to say that there's something about those 6 dimensions that's actually more about space-time, but it's actually 16 dimensions, and you get an additional 10 dimensions, and those 10 dimensions I get have a 9+1 structure, just like string theory.
Oh, okay.
I didn't want to say that those 9+1 dimensions have nothing to do with space-time.
you start getting some outcry.
I made it really cryptic. Honestly, the point of that paper, I didn't expect anyone to understand it. It was just kind of like, it's a timestamp. It's there. It took me 3 years just to get it published.
Yeah.
But anyways, so in that view of how I look at things, I look at the matter particles as having their own identity. Their own identity, their personality is defined by their charge configurations. And so to me, the extra dimensions are for matter, for defining the characteristics of what makes up these elementary particles. And if you go back in history as well, there's a book by Hermann Weyl. I haven't read it. I should read it. And he said space-time matter is what it's called.
What's it called? Space-time Matters is the book?
Space-time matter. As if it's all one word or something. Maybe there's hyphens.
This guy, Hermann Weyl.
Yeah. So, I mean, that's a hint right there, right? Okay, he separates with commas, right? So, but space and time got unified into space-time, right?
Right.
And now string theory is trying to, it's not just a theory of quantum gravity, they're trying to get unification of all of the fundamental forces. So these extra dimensions are going beyond space-time to include space-time matter.
Oh, that's cool. Wow.
And that's how I look at it. And I mean, that is kind of how the string theorists look at it as well.
Nice. All right, let's go to our next question from our next guy. Let's see, the Michikaku thing. Or sorry, QVNTT says, okay, with the increasing interest in space exploration, are there potential applications of your research in understanding events like dark matter and dark energy? Also, what first sparked your interest in physics? I was really never a science guy. In fact, chemistry haunts me. Yeah, I've got a bad teacher for that. But I want to know more about physics. I wanted to get into it, but I don't know how to start. Is there any tips of how to get into physics?
Yeah, that's interesting. I mean, for me, I'll just kind of tell my story of how I got into it and then get to the more technical aspects. So
sure.
Originally, I didn't really know what I wanted to do for a while in high school, even before that. I mean, I was good at math, and people just sort of say, oh, you should be an engineer. And so when I was a kid, it's like, what do you want to do when you grow up? It's like, I guess I want to be an engineer, but it's like, I didn't even know what that word meant, you know? It's like, what is an engineer, right?
What's an engineer?
I don't know. But I guess I want to be one, right? And so I actually liked chemistry originally. I don't know why. I just thought it was
I like chemistry too. I think chemistry is really dope.
But it was kind of before, like, I don't know how I got into it a little bit, but I don't know. I just like the pH strips and just thinking about how, like, you could form atoms by putting stuff together. It's just kind of a cool concept to me.
It's like baking.
But eventually I kind of, I don't know. So chemistry was cool, and physics, it wasn't like I loved it at first, but I was okay at it. I was decent at it. And it just kind of turned into this thing where over time, why did I get into it? Well, what happened was I ended up taking this summer minority program at MIT my junior year in high school.
Okay.
And they just exposed me to this really hard physics class. So
they were just like, we're going to hit you with it, dude.
Yeah, they told us about multivariate differential calculus for wave equations, which is like, it's like the third semester of college physics.
And you're doing this as a junior in high school.
As junior in high school. So I had just taken, I was able to get ahead of the game. So I took a calculus class in my junior year. So then they saw that and they're like, "Oh wow!" So it was a little.
Do you remember what it was called? Was it called MITES? Was it this one? Was it MITES
Yeah. So I did that program. Yep, okay. MITES. And so I was just exposed. Honestly, it was that whole culture environment. So in high school, I didn't even get amazing grades. I wasn't a straight A student, but I would always challenge myself. I would take the hardest classes. Yeah. Sometimes I would fail. Not literally fail, but honestly in high school I got more B's than A. So I would get an A in math. I would usually get an A in science, but then basically everything else I would kind of get B's. I also wasn't really someone who would like try to do my homework. Like I didn't really study. at all. Really.
I know
Like,
we were just gifted.
lazy.
We were just able to get through it.
Yeah. And like I could have like applied myself more. It wasn't like I was just, it wasn't like I was just born. I just had this passion.
Yeah.
It really did develop over time. So I mean, I say that because it can happen to you where maybe you go to college and something just sparks your interest.
Someone just hits
Maybe
you,
you've been
yeah.
in high school your whole life and you just see something different. Like you certainly will experience different things when transitioning from high school to college, and it'll kind of open your eyes. So for me, what opened my eyes was I was just in that environment, and for whatever reason, I thought that I would go to this program and not be that good because I already wasn't a straight A student, and now I'm competing with, the smartest people in the world or whatever. So, but it was like I was there. It was the summer program where it's all about, doing school in the summer.
Okay.
So everyone, and it was this culture, this environment where it was like cool to work hard. So I really pushed myself and kind of developed my passion there. And that's really where it all started. And it was kind of wild because I was learning, like he was teaching us physics using math that I hadn't even learned yet. So he's having to teach us the math and show us.
Like on the fly, you're building the plane while you fly it.
So exactly. So honestly, it just got to this point where I did find it interesting. I mean, just seeing how ubiquitous, like this concept of waves, it's just so universal. It just kind of blew my mind. I mean, when I learned how waves work, it literally just, it did something to my perception of reality. Like when I would look at water, it was almost more beautiful to me. Like I could appreciate how things waved and why at a deeper level. And for whatever reason, it's just, like I wasn't really as a kid, like into nature. It's like, oh, okay, whatever. Yeah. Like there's a tree there. Like I know what a tree is.
Yeah.
But then I don't know. Same with water. It's like, okay, yeah, the ocean. Yeah, I like jumping in the water. It's fun to swim around in the ocean. But like, I don't really like going for walks on the beach. But once I kind of learned how waves worked, it somehow sparked my interest where I would look at the water and just like actually pay attention to all the details and be like, wow, like I kind of see how the math, like I could imagine how these things actually could come from this math in a way. And so that really did spark my interest. So let's see,
I think the summer
the
programs is a good idea, and I have a lot of kids who they ask like, how do I get into this? What do I do? And yeah, those summer programs you talk about, I think those are great. And you kids, you should apply to them. And as one of the students said, like, was it, how did you get into MIT? Was it the competitiveness? I think surrounding yourself around people who also like want to do very well, you kind of rise to the challenge. If you hang out with a bunch of losers, you're gonna be a loser. If you hang around a bunch of people who are trying to like do very well in their classes and it's seen as like cool, like you're gonna do well in your classes. Yeah.
Exactly. Yeah. It sort of depends who your friends are a little bit. That can help. I mean, and honestly, what happened was there was this spark where I was always like taking the hardest classes. I didn't really care. And then it got to a point where they give you what do they call it? A guidance counselor.
Okay.
And she was kind of like, oh, Boston College would be a reach for you. And I was kind of just like, it really, I don't know, it just like irked me where I was like, I don't even think Boston College is that cool anyways.
BU isn't even that.
And so,
Boston University or Boston College? You know what? Like even
it was
those.
Boston College because I grew up in Massachusetts. And for whatever reason, like I don't know, it was like perceived as, it's a good school. It's certainly a good school.
It's okay school.
But I don't. It's like in that state, it was like a private school, so it cost money, and like you just hear, oh, Boston College, and so like they were asking me what college you want to go to, or they had this thing where they would map out your GPA and your SAT scores, and they'd be like, this is what you can do, like, and they're like, yeah, that's gonna be a far reach for you.
Bitch, I would go to MIT. Yeah, no, good.
So another thing that happened was I was always in the hardest classes, and then for Spanish, I was really bad at Spanish. I'm really bad at languages. And so I was in honors, and then they were like, you should go to level 1 Spanish. And so it was kind of this pivotal moment where I was like, oh, should I just like kind of not stay at the top, or should I like rebel and try to so then like that's kind of when it like I was like, okay, no, I need to change all this. And I also had the option. It was like, do I want to take calculus? They were also recommending that I don't take calculus and just kind of take the whatever next class, the pre-calc class. So I was like, no, I'm going to do this. I'm going to stay at the top. And so it was something about it. It was just kind of my own ego, to be honest. But, it got me going. And so that's kind of what made me even want to apply to that class, because I was like, wait a second, if I get into this program, then if I do well at that program, they write a letter of recommendation for colleges.
to get into MIT, basically. Yeah. It's like, it's a precursor.
so that went really well, and I ended up winning basically a couple like little awards. You know, they have
like
different
best student of
awards
the
in
summer or
each class,
something.
best student, most improved,
Yeah.
whatever. And so I got a couple awards. So then I was going into my senior year, and I just knew that it was like, well, this is gonna be a slam dunk, and it led to a lot of awkwardness because the valedictorian got deferred. And so then I was like, oh, but you went to this minority program. You only got in
because you're black
and
or
not
something. Yeah.
you're half black too, which makes it even worse. So yeah, it was a whole thing. But anyways, but chemistry is a lot different than physics. Getting back to the question.
Yeah, sorry, yeah.
Chemistry, I mean, especially once you get a little more into it, it really, like, I'm not good at memorizing things.
Yeah.
But I'm good at physics for whatever reason.
You're
like,
very good at physics.
You have this intuition, like, for whatever, it's like when things make sense to me, like I can kind of derive it, you know?
I will say, yeah, my personal
time.
experience with you was when we were studying for the comps, right? And I'm like trying to memorize the formulas, and you're up there doing a practice problem in front of me, and you're like, I think there's a G here, oh, there should be something here, there should be something here. And you would just come up with the formulas. I'm like, whoa, like DC understands like the framework of all this. Like I'm just trying to memorize shit, but he understands what this all is and is able to just like derive things on the fly. It was very cool. It was a very cool moment to see that.
So yeah, I mean, I think it helps to, I mean, if you want to get in physics, you kind of have to do it because you enjoy it, because get a job doing computer stuff, honestly, like AI or whatever, like computer programming. I mean, that whole field is kind of changing now, so I don't know what to say, but I mean, you don't really like go into physics to get a job. You kind of do it because you like it to some degree. I mean, you can get a job with physics, but especially with theoretical stuff too, it's definitely not something you do for a job. So you do have to have some passion, and I think you kind of embed your passion in trying to understand how the world actually works,
right,
and gaining that intuition. And I think that's where it gets exciting, because you feel like you actually understand how things work. I remember trying to explain to my grandmother, it's like, oh, I learned like why the sky is blue, and I was trying to explain it for like why rainbows, are, and she was just like, I don't care, like why are you like the sky's blue. Like, why do you need to
fuck it,
explain
dude? The sky's
everything to
blue,
me?
dude. You're fine.
So, it depends on what your interests are at the end of the day. But some people are just kind of, they're interested in trying to understand why things work. Other people are just like, whatever, I have this thing, it works. Who cares, right?
Yeah.
So it does depend on your personality. And then the other question I thought was interesting as well. Yeah, with space exploration, I mean, I have actually published a paper on dark matter. It's pretty... Yeah, it's.
Where do we find it? David Chester,
crazy idea.
Dark matter.
You might type in higher dimensional gauge theories. Let's see.
Oh, here I got it. Warm dark matter from higher dimensional gauge theories. Is this it?
Yeah.
With Rios. Yeah, cool.
Yeah. So that was a paper we put together in about a month.
Oh wow.
And that was wild, because basically we had this free voucher for the journal, and it's like, oh, but it goes away in a month, so
we got to use it.
They had this idea that was discussed like 2 years prior, and it was kind of like, okay, now or never. Like, are we going to do this or not, right? So that is pretty wild, because it went up to 27 plus 3 dimensions.
Oh, 30 dimensions. With brains and 2048 fermionic degrees of freedom for dark matter. Wow, dude, this is out here.
So there was this dark matter researcher who was saying basically there's cold dark matter that's kind of popular in the astrophysics community, and then people study hot dark matter.
Okay.
But then there's this warm dark matter that's kind of in the middle, and she was saying that, that's kind of the third least studied area. And so she was basically saying that everyone is looking in these two areas, but no one's looking in the middle. Obviously some people are.
Oh, the Star of David, dude. I love this. I love that your name is David, and the Star of David comes up all the time in this type of stuff, dude. It's too good. It's like meant to be.
Yeah, Mike is obsessed with that. So this dark matter researcher says in her thesis, she had discovered that for warm dark matter, if you had roughly 2,000 degrees of freedom to describe the dark matter sector, that would be a good fit for her idea on what would lead to good galaxy formation. Quite frankly, I tried asking her a few times to explain it more. I don't even understand why exactly. I never got to the bottom of it, but Mike had discovered these algebras, and we had written about how one of the algebras was E8, and it had this 128 parameter object, and we had used that for visible matter. And so when you extend that to the higher ladder, it's like these algebras have this periodicity every 8 dimensions, and so when you go up to the higher ladder, there was this matter particle that had 2048 dimensions or degrees of freedom, and so it's kind of like, well,
it's a nice number.
2048 close enough? You know, is that close enough to 2000? She's like, yeah, roughly 2000. You know, probably not 3000, probably not 1000, but
does that come from? It's like
it like
2 to the 20th, right? What is 2048? 2 to the 16th or something? What is that?
That's 2 to the 11th, right?
2 to the 11th, yeah. Okay.
So, yeah, it was wild. Basically, we had these algebras that had these membranes, and membranes are like materials, like extra-dimensional objects.
Okay.
And so I made that figure.
Dude, I love this figure, dude. This is the most wacky fucking Venn diagram I've ever seen, dude.
So it's not quite a Venn diagram. It's not a Venn diagram, right?
Yeah.
These branes are extra-dimensional but intersecting.
Okay.
And so there's a membrane for the matter sector of the visible matter sector, and then there's another membrane for the dark matter sector. And each of those had a space-time sector, and the space-time sector overlapped.
Okay.
So we were saying the extra dimensions beyond space-time are for matter. And so there was like this one membrane contained space-time and the visible matter. Another membrane contained space-time and this other matter sector. And since it didn't have, since they had different matter sectors in these extra dimensions, it's dark because the light, I was saying that extra dimension for electric charge is an extra dimension on this side, not the other side. So, but the math just like popped out that they intersected by this 3 brane, which is a 3-dimensional object for space, and it can evolve over time. So it's like these, like we got this paper.
Gosh.
It was like a week. It was a week to the deadline, and it was all wrong. I get the draft. I'm like, crap. They're like, okay, David, go ahead, figure out how to unify the standard model with dark matter. And I open it. And I'm like, the standard model is all wrong. Like, I got to start from scratch. It was like, I got 7 days. Like, this is bad.
I'm about to crack myself out.
And I start staring at these algebras. And to my surprise, it's like, wait a second. If you intersect these, like, it actually makes sense. And it was a little weird because even to get this 2048 to pop out, like, it ended up making a lot more sense than I was expecting. And so it's a little like grandiose in a sense, but yeah.
That's cool.
So
someone's asking, what can we do with this? This is like, you're describing dark matter. One of the students asking, what do we do with dark matter? Like, what do we do
honestly,
with it?
I don't think it has very many applications. I don't think anyone does. I mean, if you're going into space exploration,
yeah,
on the engineering side, you're trying to, I don't know, mine asteroids to make money, right? Like,
yeah.
Like, it's not clear what dark matter is going to have to do with that. It's just cool to study, right? I mean, astrophysicists just want to know how the universe works, so we want to understand what all the...
And a lot of the universe is dark matter, right? Most of it is dark matter, the universe.
Yeah,
so it's like what's going on?
It's so elusive that it's hard to fathom how it's going to be used for engineering. I mean, really at the end of the day, figuring out propulsion without oil in general, I think
that's where we got to get into that. Yeah, your anti-gravity stuff. That's going to be the fun stuff. Yeah.
So yeah, I mean, at the end of the day, yeah, dark matter and energy is out there, but I don't think space exploration. I mean, because dark matter, it's too. I mean, you're taking information in from different solar systems and galaxies and whatnot.
Yeah.
Dark energy is the subtle energy density that's everywhere. We kind of understand about the acceleration of the universe, the visible universe from that, but I mean, it's going to take us just because. Let's say we perfect how to get to Mars, like we're still not getting to another solar system. So
yeah, bro. Yeah, even if we travel at the speed of light, we'll be like dead before we get there. This is where you need like wormholes or like faster than speed of light travel, like warp stuff.
Yeah,
that's about to get nuts.
Yeah. So yeah, cool questions. Was there any other parts of that?
I think that's good. Let's move on to the next one.
Yeah.
Let's go to the next one. All right. Next question is from Equity. It says, as a freshman in high school, what classes would you recommend I take about the intricacies of the universe and maybe study theoretical physics in the future? Also, as a theoretical physicist, what do you do day to day? Oh, that's good. Is it a boring job or an exciting job? And would you recommend young people pursue a career in theoretical physics?
Okay. Well, I mean, as a high schooler, a freshman in high school, I mean, I guess mathematics, right? Just try to get as ahead as you can in mathematics.
Those are the tools you need.
That's going to be the foundation. To solve physics problems, you're going to have a solid grasp on math. So just keep everything in mind. You know, when you're learning, and that's the problem. Sometimes when you learn math, they don't really teach it in a way where it seems useful. They're just kind of like, do this math problem, and you're like, what's the point?
Yeah.
Well, it's gonna become more and more useful over time, and it's gonna be too difficult to really grasp that. So just try to have some patience and learn your mathematics, I would say. And you might be able to take a physics class if you do. Here's the thing: if you do really well in math, you're going to be able to take physics earlier. But if you're kind of struggling in math, they're going to be like, nah, maybe you should wait on a physics, wait till college. But
Yeah, because you need the calculus to do physics.
Yeah, so if you could get to calculus as early as you can, you know, not freshman year, but that will help. And you can take some physics without calculus, but it really, I mean, Newton invented calculus to solve physics.
Yeah, it was his tool.
Physics, so
yeah.
So that was his tool. So yeah, I would start there. And in terms of what I do day to day, I mean,
yeah, what's your day to day?
Well, yeah, I mean, I actually did just switch jobs. So now what I'm trying to do is identify how this certain device works. So trying to understand the fundamental principles of what physics could even go into this crazy device that they have. This device is basically flying, and no one understands how or why it can fly.
We're gonna have to.
So my job is essentially to figure out how it's flying and what are the principles behind it. But I mean, I do this thing where even in my last job, it was research based, where I'm constantly downloading papers. I'm skimming them. I'm not reading them. I'm skimming them. I'll open it. You know, when you start doing into research, it's really difficult at first to read these papers.
Oh yeah.
But I found after doing it a few years, like at first you kind of have to read it, and there's all these buzzwords, all this technical jargon, and you don't know what any of it means. But you have to get through it. So you almost have to kind of realize there are these words and kind of put a black box around it.
Yeah.
And just kind of, all right, this black box interacts with that one. I don't know what it means yet.
Yeah, I don't know what's inside the box, but the big picture.
You might spend a month or a whole summer just reading one paper.
Oh, yeah.
At first, but you keep doing that and you get better. And you pick a subfield. You start taking classes in graduate school. You start learning about your specific field of interest, and then you start. It's really intimidating the first time you go to a conference because now it's this whole other level beyond teaching, right? When you're in a class, they're teaching you the thing in the textbooks that's been established for 30
been discovered,
years
or more, hundreds of years, thousands of years. Yeah.
Now you're taking these graduate classes, and then you go to a conference, and they're talking about the modern research in a paper that just came out a week ago that won't even get in a textbook for another 30 years.
Yeah.
And so it's really intimidating. I remember I felt it's soul crushing because these people are so smart and you just have no idea what they're talking about. And you're just trying to not look like an idiot. Like if you're asking a dumb question in a class, imagine asking a question at a conference now.
Oh yeah.
But eventually you go to your second conference. You're like, okay, I heard most of these buzzwords last time.
Yes, exactly, yeah.
It starts to get more familiar. You start to get better at reading papers. Eventually, I got to this point where, in a certain way, it doesn't happen with all papers, but with some papers, if it's in the right direction, I don't even need to read it. It's just like, I look at the abstract, I'm like, okay, they claim to do this, skip it all, like, go to, where's the important equation? I just kind of skim the math and see if it makes sense to me. And then I catalog it. So I spend a lot of time just downloading papers, putting it in subfolders based by topic.
Yeah.
And then I try to come up with projects, basically. I mean, you could try to just make your own theory, but at the end of the day, no one cares about your own ideas. Like,
you have to build on others, right?
Yeah, the whole point of doing science is, I mean, do you want to write a paper for yourself? Do you want to write a paper that you want to read? Well, I mean, you can do that, but no one's going to want to read it. Like, the whole point is you have to consider your audience. Any type of communication, you have to consider who your audience is. And you want your scientific peers to read your papers. So it does help to get embedded with trying to identify, well, what do they care about, right? So I try to find a balance of what are my interests and what do other people care about. And I try to identify what's my skill set? What do I know that I think
what's
I
my
have an
specialty
edge on
what am I the best at? Yeah.
And so maybe you see a paper that just came out and they're talking about some hot new thing, but you actually studied this other thing that's from 10 years ago that no one's really looking at. And you realize, like, a lot of times, a lot of science is done by kind of putting things together, synthesizing. And so you can kind of create a new idea or get a new solution by combining two methods. So that's what I do a lot. It's like trying to come up with ideas of what would be a cool computation, what would be a cool like theoretical framework. So some days, like, I mean, I just go home and will like just start writing down all of these equations, like
looks like hieroglyphics, dude. Sometimes I'm just like, what is he writing?
Yeah, so
and you still use like pen and
out,
paper. You use like just like pen and paper.
Do a lot of pen and paper, but I also do a lot of computer too. So Mathematica is this programming language that we use. So sometimes, for my last job, I was doing a lot of simulations. So it would be going into extra dimensions and getting these polytopes in extra dimensions and projecting them to lower dimensions and figuring out how to rotate them and transform it. But honestly, like even it got to a point where I'm so obsessed with this stuff, I'm coming home and just like I have folders and folders of all these notes, like handwritten notes, where it's just like chicken scratch of Greek letters and equations. And so, I mean, on a day-to-day basis, yeah, I mean, there's some communication involved as well, communicating with different people, maybe having meetings every once in a while. Yeah, kind of maybe you do a collaboration, you'll have a weekly meeting. You kind of talk about, okay, what are the next steps? Maybe we're working to publish a paper. That's kind
I think this is what you talked about, right? There's a big goal, and then you have a bunch of like small goals to get to that big goal, and you're just constantly evaluating those.
Yeah, and that's another tip overall for like, getting into physics. It's like you kind of want to break it down into pieces. Well, I don't understand how to solve the whole thing, but if I solve this toy thing first, that will kind of lead to the next thing. Or can you break it down? It's like creating a route. Like you want to go do all these things. You need to go to these 3 different locations. I'm going to go here, then here, and then here. I mean, solving a problem is very much like that, where it's kind of like, well, I need to maybe have an introduction. Maybe I just review the formalism.
Sure.
Of what are the tools I need to work with. I'm not even solving it, but just establishing the framework. Then, leading into it, okay, we need to solve this thing to establish that and then derive this result. Another good tip is when you're trying to do something new, you first want to, it's like you have to have the method in mind for how you're going to solve it. And you want to first apply that method to a solution that's already been done.
Yeah.
So that you're on
you
the
can
right
verify
track.
it. Yeah. Validate.
Verify that validate that this method works for something that's already known, and then use that method for something else. And this works beyond theory too, right? You could do an experiment, right? Let's say you want to discover some new effect, right? Or whatever, you want to do some experiment that no one's done before. Can you find an experiment with the same lab equipment that you can first test and be like, okay, if I do this gets this result that everyone knows about. So you can kind of validate, yes, like I know how to use this lab equipment. Now I'm ready to use it on something that someone else hasn't done. So I am trying to get a little more experimental, but I'm going to start by working with these engineers and talking with them to figure out, okay, what do you think? How do you think this thing works? And they'll say, oh, I heard this buzzword about solitons.
Solitons? Oh yeah, I've heard about these. Yeah.
They'll just. So then it's like, well, but how are these solitons created? Is there any reason to think? There was this other one where someone's like, oh, I think there's this resonance between these particles and these neutrinos, and it's just like, well, but why would neutrinos even be? To an engineer, it's like they don't know where neutrinos exist. Like, they're trying to say these neutrinos would have an engineering application. I'm like, well, I don't know. And they're like, well, I read this paper. It's actually in this legit academia paper. So now I'm going in and I'm reading the paper, and it's like, okay, well, they actually have some serious math here. So it seems legit, but maybe, it was written 50 years ago. Now we know more about neutrino physics. So I'm currently evaluating if that paper makes sense. Right. So it's like, okay, there's this patent on the internet claiming that this is how this device works, but is it how it works?
Yeah.
So that's kind of what I'm getting into now on a day-to-day level.
So they say, is it boring or exciting? I think it's exciting. Sounds like you're very excited. You're not very bored with what you do.
Yeah. I mean, it's interesting because at the end of the day, everything still is politics. So it is very exciting, but it also it can be emotionally highs and lows sometimes. I mean, especially with theory, because it's so challenging where some days you just feel like an idiot where it's like, what am I even doing? Like, I
Hey, listen to this, kids. Even a quantum gravity guy feels like an idiot sometimes. It's okay. It's okay to feel stupid.
Yeah. And so honestly, I kind of do that when I approach problems too. Like, the quickest way to solve a problem is guess the solution and then prove it's right. That's kind of one thing. But another thing I'll do is I purposely get overly ambitious one day, and that's when I get more creative. So when I try to solve something, I hope for the best, and that's when I try to think of all the crazy ideas, even if it sounds ridiculous. Just, maybe this could work. And then the next day, I'll kind of say, yeah, but let me be super skeptical and pessimistic and try to debunk my own idea, right?
Yeah.
Try to poke holes in it because other people are going to be poking.
Yeah,
holes in it. So,
they're gonna test it.
You kind of have to oscillate so that there is this roller coaster effect where one day you think you discover something big, and then the next day you look at it and you're like, oh, that was completely wrong.
Yeah, you're just
and
like, oh.
Just that idea of you felt like you were on the right track, and then you realize you weren't. That's but honestly, at the
be a
end
little
of the day,
demoralizing.
it's still fun.
Yeah.
But then also, the politics at the end of the day, how are you going to get paid to do what you're going to do? Is it going to be, applying to grants? Are you going to be working for some boss who's funding something? And then one issue I ran into is it was almost like I was so close to doing what I wanted to do that it felt like it should be a passion project, but it was still like, it was so close to what I wanted to do, but just like a little bit different. And that, it was to my surprise, it like frustrated me a lot because I felt like I could be excelling more and more, but I felt like I was kind of being held back in a way. So, I mean, I just started a new job 2 weeks ago, so I'm kind of in that excited phase to...
Yeah, it's something new. A
new experience. So
it's awesome.
Yeah.
So, okay, let's go to the next question we got. Dun, dun, dun. Dark aspect. What does quantum gravity mean to you? Have you discovered any secrets about this world? And have you done anything groundbreaking in your research? What are you researching right now? Can you create light and dark matter in a lab or something? And what do you think about UFOs?
Oh yeah,
and how was your day? There's a lot. Just pick some of the fun stuff that we haven't talked about yet. But yeah.
I love all of this.
Okay, do them.
Well, quantum gravity to me, it's basically what is the high energy theory of physics when things are really big. That's one way to look at it. There's going to be regime. I mean, some people are saying, oh, is it about discretizing space-time? I mean, we don't know. At the end of the day, we know that there are certain experiments you could do where quantum mechanics and gravity should be important. And I mentioned neutron stars. Or black hole scattering. If you had two black holes and they collide at high enough energy, you will get to a point where quantum mechanics should matter, especially for neutron stars, probably. So, I mean, to me, quantum gravity is the theory that describes these high energy processes that basically probe stuff on small scales, yet there's enough energy around to get where gravity matters, because energy is kind of like mass. So, we don't really feel the gravitation between human beings. Like we feel it to the Earth because the Earth is so big. But on the other hand, we don't get down to the quantum scale with the Earth typically. So, but imagine you had two stars that are just like colliding at such a high energy that they get extremely close. I mean, there's a chance it could happen one day. So that quantum gravity could describe something like that.
Yeah.
And that's how I look at it. It's just what would be the theory, or another way to say it is, what is a theory, that can describe quantum processes and gravitational processes, or a single framework where you could take the limits, right?
Okay.
So maybe you have an experiment that only quantum mechanics matters. You have another experiment where only gravity matters, but you have this theoretical framework where you can take that limit to this direction and that limit to the other direction and have this theory describe both experiments. That's what we're after with quantum gravity. So,
dope.
Have I discovered anything?
Any secrets, bro? You've discovered so many mind-blowing things. Secrets of the universe.
I think I have figured out some nice things. So one of the papers that the six-dimensional one, I mean, that was cryptically trying to figure out how to fix Garrett Lisi's unified field theory.
Right.
So he was obsessed with this thing called E8, and E8 gets used in string theory as well. So it's kind of strange because everyone was like, oh, Garrett Lisi wiped out. Basically, he had this paper that had a lot of errors, but it had a really catchy title.
Oh, it's beautiful, dude.
And
E8 is always so pretty, dude.
So it's mathematically beautiful, and it was used in string theory, but he was kind of hating on the string theory. So what I'm actually trying to do, Mike Rios is a collaborator of mine. He kind of pitched this idea of how to kind of bridge the gap between Garrett Lisi's model and string theory. And so that's one of the big things that I've been doing. And it's kind of funny. I finished this paper that's with a journal right now, and the archive is a preprint website. They literally rejected it, which is pretty strange. Because
yeah, one of the kids was asking about archive.
Paper,
I said you can just post whatever on archive, right? But stuff gets rejected from archive. I thought it was like you.
It's not supposed to. The whole point of it is sometimes it takes a while for a paper to get peer reviewed. So
sure,
it turns into a debate. If two people publish the same thing. What if some person discovered it first, but it got published after, right? Then it's like the person who published it first would get the credit, even though it was discovered first. So that's kind of an oversimplification, but that's certainly one aspect of it. So you have this preprint website where you put it there and it's live instantly, and then you submit it to a journal. But since this guy, he blew up basically, and he got really popular, and everyone was talking about it, but then everyone felt like he got too much attention because
this is the politics.
Science Channel.
This is the politics we talk about, right?
And so now it's kind of taboo to talk about E8 unification, but string theory uses E8. So like there's literally a paper where Ed Witten talks about M theory as being an E8 gauge theory. So but then most of the string theorists like don't even know about that. Like so it's like this weird thing where you go into academia and the string theorists are like, oh, this E8 is garbage. But I mean, heterotic string theory also uses E8 cross E8. I mean, they know about that, but it's different. And so basically, that's kind of the main thing that I'm figuring out is how to actually figure out the rigorous details of the physics of how such a theory like that should work. And also, though, I'm interested in electromagnetism and exotic forms of gravitation. Those I think I've kind of found some things, but I don't want to toot my horn too much, but basically differential geometry, trying to figure out how to rigorously define the mathematics of exotic differential geometry that is what I realized is that when you look at space-time geometry and you look at curvature and general relativity, it's actually the most macroscopic type of differential geometry. And so what I've realized is to get to quantum gravity, we actually have to first finish studying classical gravity.
Okay.
And everyone's just trying to quantize GR, but it turns out there's this other differential geometry called torsion and non-metricity that it's still classical, but it gets more granular. And it gets to a point with non-metricity. I thought I discovered this, but it turns out no, some guy discovered it. And no one had written about it in the gravitational context, but he was studying relativistic elasticity theory in like the 60s or 80s, certainly by the 80s too. And he discovered that you can add a point defect. You can add or remove a point from space-time itself, which is literally the smallest type of form of gravitation that you could have. And everyone hates this geometry because it's really weird to think about. But my whole thing, I think that's kind of, before we figure out quantum gravity, we need to actually understand the smallest forms of classical gravitation, so then we can understand how to, study gravity on a small scale.
Oh, super.
So
cool.
that's kind of what I'm excited about. Let's see what else was mentioned in there. I could grab a diode and put it up to a battery and
creates light
that way.
Yes.
But I don't know how to create dark matter. I mean, I have an idea of what dark matter might be, but honestly, I don't know if it's correct. It's just connected to this grandiose mathematics. It ends up relating to the Leech lattice and the monster group, which is like really deep mathematics. So it's kind of cool for if you're kind of a mathematical physicist. But at the end of the day, there's so many different dark matter theories out there. I'm not super into dark matter research. I don't know how to. I don't think anyone knows.
It's a buzzword. People love the word dark matter. Just like, ooh, dark matter.
Yeah, it's mysterious. It's mysterious. And then,
what do you think about UFOs?
What do I think about the UFOs? Well, I mean,
I think they're real.
I think there are objects in the sky, and I think that they have been. I think that there's basically people after World War II. Let's say black organizations, kind of private contractors,
Skunk Works,
convince the military it's not worth their time to have the government chasing after UFOs. And so I believe that a lot of the stuff we're seeing could actually be man-made, in my opinion.
Oh.
I think there's probably a mix. There could be extraterrestrial stuff, but
You
I
think
it's
most of these
highly
images they
possible.
find are just really far out things that technology that we haven't disclosed, I guess, disclosed yet?
Yeah, I think there are sort of private contractor companies that have information that is in these compartmentalized projects. I mean, Bill Clinton himself, as president of the United States, tried to figure out what's going on with the UFOs,
Yeah.
and it got to a point where he was told that he didn't have the clearance to know.
The president
So
doesn't have the
it's
authority?
at the point where, okay, it's kind of outside the government, but they're
What's
kind of
higher than the
contracting
government
with
then?
the government.
It's like
Exactly. So
what is
there's
this?
this guy Stephen Greer who's, I mean, he's a character, but he actually was an advisor to Bill Clinton, and he's collected a lot of documents from whistleblowers for years, going back 25 years now. And so he basically he did this thing that was really ballsy. He had got all of these this secret information that was classified, and he wrote a letter to these organizations, and he said, basically, all of this stuff is illegal because and he basically found some stuff that's illegal,
Yeah.
and he says, I have whistleblowers that are willing to testify in front of Congress.
Oh wow.
So therefore, since your operations are illegal, it's not classified, and I'm going to release them to the public. And I'm letting you know now where, you know, if I'm letting you know, if you don't say anything back to me, I'm going to start releasing this information. And he's still alive today. You know, he hasn't, you know.
They haven't taken him out yet.
So he's done things in a very, I mean, he also, it does get weird because then he's also like into all this free energy stuff. It's super weird. Like, I originally didn't care about UFOs. I was actually kind of more interested in the energy stuff. My whole thing was maybe the quantum vacuum could lead to maybe like quantum field theory could be useful for engineering one day.
Okay.
That was just my hope. It's like, what's the point of science? Like, I don't think it's really useful if you just, it's like, oh, look at me, I know all this smart stuff. It's like, you know, some scientists, they're just motivated.
What's the
they
practical
want to
part?
understand for themselves, which is cool. You know, a lot of good things are discovered that way, but I don't really care that much. I mean, I am kind of curious, but what really motivates me is to see how this stuff could affect the real world. Like Nikola Tesla, it's just cool how we have alternating current from what he did, you know?
Yeah.
And so I just think that's interesting. And so I always liked, you know, I set those unrealistic long-term goals that are ambitious. And so I was kind of thinking, well, most people don't think that quantum field theory is going to be useful in their lifetime. But what if it could be, you know? I mean, there's surprises all the times. When people were discovering quantum mechanics before computers were invented, you know, they're thinking it's just like these tiny particles. What could this have to do with reality? And it's like, well, look at computers, right? Like it became useful in surprising ways. So
Right.
I was kind of banking on that. Maybe there'll be a way where, I mean, it's kind of a play on words, but we're high energy theorists. So, and I didn't even care about global warming that much or energy crisis, but I care about people, and people believe that there are these problems. So I find value in trying to find those solutions. And so, but then when I started looking into a lot of this like energy stuff, then it was like the same types of people, they start talking about UFOs, and I was like, I'm not trying to get into that. Like, why? It's almost like once someone's kind of crazy, they're crazy about everything. But then I started to realize, oh, I mean, if you did have these craft and you were, if you were shooting down UFOs, or if you were, is it Robert Bigelow? I mean, Bigelow bought some land
Okay.
that had UFO crashes on it, and he was trying to and then it turned into a whole Skinwalker Ranch thing. Like a bunch of paranormal stuff started happening and got super weird. But he was originally just trying to figure out how to reverse engineer these UFOs because he has an aerospace company. So
Yeah.
you know, it kind of makes sense. So you're trying to reverse engineer these things. How are you going to power it, right? What
He has an institute for consciousness studies, dude. What who is this guy, dude? What?
Yeah, so I mean, he has an aerospace company
Yeah.
as well, but you know, because that's the thing. It starts once you start getting into some of that stuff, it gets
This guy looks like a Marvel
paranormal.
character or something, bro, dude. He looks like
Right?
he
Yeah.
looks like a villain from like the next Avengers film.
Yeah, so I mean, over time, like I'm also the type of person I don't like to just reject things. Like I like to take in all the information I can. I mean, even if something's unlikely, I'll hear it out. I don't know. So I'm kind of the guy where people will send me their crazy ideas, and most professors wouldn't reply to it, but I'll be like, let me look at it. Like, and let
Yeah,
me
there
tell
might
you
be something here.
So with all this UFO stuff, it wasn't like I was super into it, but eventually once I started absorbing all the information, things started to click, and then I started to realize that some of the gravity, exotic differential geometry, it's torsion, for instance, it's sourced by spin density.
Okay.
And spin density is basically angular momentum divided by volume. So if you have a really big volume and you put it in the denominator, it's going to get really small spin density. And so no one's really detected this torsion. All the astrophysics, because gravity has to do with the big stuff, right? So, and they're looking into space and they're like, we don't see any torsion. And so I've kind of gotten to this point where I've realized for this torsion stuff, it's also hard to find in the laboratory, but I think it could apply to condensed matter, like small elementary particles, because they have quantum spin, and particles are almost point like a very small volume, so that gives them a high spin density. So these exotic forms of gravitation that I've been obsessed with, it turns out might actually be related to describing new ways to interact with gravity. And this torsion is actually kind of anti-gravitic in a way.
Someone's asking, like, what
exotic.
is spin? What is spin? Is it literally like things rotating? Like, I've always just thought of it's like why is it 1/2 minus 1/2? Like,
yeah. So it did start with this idea of rotation, right? So you have angular momentum, but once it got into quantum mechanics, there was this thing called intrinsic angular momentum or quantum spin. Same thing. So they were still able to model this particle as being a point. And if you have a point, like angular momentum is r cross p, where r is like the radial position. You have a lasso and you're spinning around that has some radius.
yes.
And then it has some momentum, some mass times velocity. So if your radius goes to 0, there's no classical angular momentum,
Right.
Because r cross p would be 0. But if they're studying these things, they think the electrons point like, but it still seems to have this intrinsic quantum spin that has the dimensions of angular momentum. So once they introduced quantum mechanics, then they started playing with this idea. Well, is there just somehow this fundamental quantum spin that it's like angular momentum, but it's just different and it's just there? And that's kind of one of the main interpretations, but we still don't know the exact structure of the electron itself. I mean, it could very well have some finite size. And that's another mind-blowing thing. It turns out that this torsion essentially creates this, like, the fact that it has mass and it is the fact that it has this intrinsic spin and it has mass, but it creates this little anti-gravitic bubble that gives it a little bit of finite size. This researcher named Nikodem Poplavsky has discovered this, and it actually fixes some of the other infinity problems with QED, quantum electrodynamics. So there's this example of gravity actually helping quantum field theory, but a gravitational researcher discovered this. So the entire quantum field theory community, all the quantum people, they haven't really paid attention to this.
Okay.
And
so they're not in their camp. Like, you're not part of our group.
Yeah. So it's just obscure, and he kind of doesn't cite many people. So it's like kind of hard. You'd have to know.
This is the politics. This is all the politics
to find it. Well, it's not even politics. It's just like there's so many papers now, right? Imagine you're Ed Witten and you write a seminal paper and you get 1,000 citations.
Wow.
Great. What do you do? Like, are you going to read all of those papers and figure out which of the best ones are? No.
Yeah.
What are you going to do? You're just going to, I'm going to read 10 of them maybe, so who's at the good universities, right? You have to come up with, because
you have to, you only have so much time.
Beings. We only have so much time. Yeah. And people like Eric Weinstein are like, oh, there's been no progress in 50 years. It's like, dude, what's the last paper you've read?
Yeah.
I think what it is you haven't read a paper in 50 years because you don't know how to find the good papers, because it's like there's so much noise that it's hard to find what's good out there. So there's an explosion of progress, but you can't understand it unless you're like really in there.
This is maybe where we need AI to help, right? AI to summarize like what are the big things that are happening.
Exactly.
And
And that's actually why I spend so much time organizing the papers that I download, because I actually had this vision where there will be a day where AI is going to read this. So if I catalog it, I can use that to train the AI. I haven't done that yet, but it's I'll get to it eventually, maybe another year or two.
Cool. Dope. All right, nice. I think that's all of his questions. That was good. Let's go to the next one. Who do we
I'm
got?
having a great day as well.
Oh yeah, how's your day going? He's having a great day. Yes.
That's dope.
Awesome. Thanks, Nick, for that question. Obama says, as an upcoming senior, should I take AP Physics or should I just do it in college? And then, what are some interesting experiences you had as an entrepreneur? I think someone else in the chat also asked about Strain Genie. And do you believe that AI could be useful for college students? Why?
Oh yeah. Well, I mean, it's at the end of the day, it's up to you if you want to take AP Physics, but why not? Right? Why not take it? If you're interested in science, then I would say if you have the ability to take it because it'll give you an extra edge. Depending on the college you go to, you might be able to pass out of that class or
let you like go ahead.
And you're going to master it even better
Yes.
than your peers. And then you're going to go into college and have this edge that some other people won't have. And you're going to be able to propel yourself further. So yeah, why not? If you can, I'd recommend it. As an entrepreneur, yeah. So it was interesting. I was thinking about a backup plan and I was in graduate school. I had kind of a rough graduate experience and I was getting to this point where I was worried that I wasn't really going to publish anything big. And so I was like, well, crap, what do? I need a backup plan. And
I got to pay
back
rent.
then, before AI wasn't the big buzzword, then it was data science.
Yeah, data science.
Especially if you had like some computational skills. Oh, data science, McKinsey Consulting is saying there's going to be all these data science jobs, but no people with talent. And so I kind of did this thing where I thought about trying to combine buzzwords like, okay, then cannabis was coming on the scene. It was like, oh,
weed was big.
Cannabis companies. So I was in California. So I was like, okay, how many data scientists are there in the cannabis industry?
Mm-hmm.
Let me try to become the world's best data scientist in the cannabis industry. Like by kind of combining these hot topic buzzwords, I'm able to isolate a more specific niche and kind of focus in. And so, yeah, I just kind of got lucky there where I was just like, well, what should I do? Let me make a database of different cannabis strains. And then it turned out that Gio actually introduced me to his friend Nico.
Mm-hmm.
And Nico, I started talking to him and he's like, oh yeah, by the way, I have this cannabis startup. It's an online marketplace.
Yeah.
But we just don't have a strain database. And I'm like, what? Like,
What?
I literally just made the world's largest strain database like a month ago. And I had no idea what to do with it. I was like, maybe I'll just make some crappy website and just get like ads, just put.
What's that website everyone uses for the strains? What's that website everyone uses? Was it?
Leafly.
Yeah, it's Leafly, right?
That one was cool.
Leafly? Yeah, this was it.
I don't know if people still use it. I mean, I'm kind of out of the biz, so to speak.
I thought there was something where, it was this. Back in the day, this was it. You're like, oh man.
That was where you'd go. Like, yeah, they had all the data on like, this makes you feel this way, that makes you feel that way.
But everything had like 5-star reviews. I didn't ever see anyone like, everyone was always like, this is the dankest weed. This is the dankest weed. I'm just like, because everyone was just high reviewing these things. I'm like, yeah, it's weed. Like, of course.
Yeah. So, I mean, I would try to apply data science to these things. For instance, I would run clustering algorithms of these strains based on the data that I could collect off the internet. Obviously not off leafly.com, but general websites in general.
General
websites. You can find information. I would try to correlate all of that together. And so what I ended up doing was so like I was saying, first before you do something new, you want to validate it. So I wanted to test if I could run these clusters, break the strains into two groups.
Yeah.
What would those two groups be? And I was
indica
curious to see my
sativa,
hypothesis. Right? It would pick up on indica and sativa. That was my hypothesis. But I didn't give it the information if it was a sativa or an indica. But I had that data as well. So then I ran the clustering algorithms, and then it turned out it's like, oh yeah, like this cluster is predominantly sativa, and this cluster is predominantly
that's cool.
Indica. And then so it's like, what happens when I do 3 clusters? And then it kind of got the hybrid.
Did it get the hybrid?
I tried to. Yeah. And so then. Like there was this idea that, cannabis is expanding, so there's going to be more people that are newbies, and it's like, what does sativa even mean, right?
Yeah.
So if you're trying to brand something, you should kind of make it more relatable. So that was kind of the idea was, can we figure out these different activity
And this is all the
groups
things of
how it makes you
23andMe
feel?
too. This was all real big. People love doing these genetic things, being like, "Oh, am I predisposed to this?" Like blah blah blah. And like you guys just did this with weed, basically.
Yeah, exactly. So, I mean, it started originally, I was just trying to understand these cannabis strains and what differentiated them and how to label them in a more human relatable way. So we came up with these activity groups, where it's like energize, create.
Yep.
And so it turned out like what I realized from and I also looked at terpene data. So like indicas were kind of more one-dimensional, but it turned out that the terpene profile of sativas was more diverse. And so I kind of had sleep as like a deep indica, then chill as kind of like relaxing, and then elevate as a hybrid. And then I had to kind of represent that diversity. I split sativa into energize and create. Or you could also look at it as kind of like body and mind to some degree, like
Right.
kind of like creative mind, like energetic, more body.
Or do you just want like
And
more of
so-
a body heal type thing? Yeah.
Yeah, so it was just kind of cool to kind of be at the forefront of, I don't know, applying this, computer science techniques to this popular industry. And then eventually we started playing with maybe even making products branded around those activity groups. And then eventually we made this DNA test kit that was basically collecting a bunch of research papers on different DNA snippets and SNPs they're called actually, and figuring out basically how the different cannabinoids and terpenes would interplay with those different things, and trying to recommend products and strains based on your DNA. I mean, the main one is actually was like there was a certain liver enzyme deficiency you could have. So
For edible
that would
metabolism.
Right. So some people, you actually, like 20% of the population actually has a bad response to edibles.
Oh,
They
wow.
have a hard time breaking it down. So they just get like really high, but almost in a bad way. So, and that you can pick that up in the DNA. So
That's
sometimes it was more like you could recommend what not to do.
Yeah,
Right?
like
Maybe you have your,
I just tell everyone don't eat
Stay away from
edibles
this thing.
because you'll get fucked up
Yeah.
on edibles.
but it depends. So yeah, it was a cool experience. I mean, there was a lot of challenges with it just because it was, from the outsider perspective, everyone's like, wow, this is such a hot industry. You must be doing really well. But it was, there were so many thorns with it, just all the legal regulations. Like at one point, our lawyer told us you can't work with 90% of the dispensaries. It was like, there was this like gray area market. So it was, as things were getting more legal, they had the medicinal forever in
permits,
California, then they
FDA.
were legal. And so they would pass these laws, but then the government, it was like, okay, now that the law is made, you need to actually create the regulations. But the government had no information on how to regulate it, because it's like, people in government don't know about cannabis. So it just delayed everything. And so they're kind of like, well, you can't really follow the laws yet, but we're not going to really enforce it.
This is the Wild West.
Dispensary, it was called like gray market, where it's like they were doing that, like they're doing everything they can, but they literally technically can't follow the law that's passed because they haven't done, the government didn't do their job yet. And so then our lawyer is kind of like, we're doing other things where we're just trying to work with them. But then it's like, they're like, oh, but that's a liability, because we were working with dispensaries in different states. So it's one thing if you're just a dispensary, and that gets into the whole banking thing, right? Because
Weed companies just could not get a bank.
It's not a big deal. But I mean, even to this day, even if it's still, scheduled at the federal level. So that, now CBD, did that go off schedule?
I thought it was like Delta 8 or Delta 9's okay or
is,
something. There's all these deltas now. I don't even understand.
Yeah, right. So now CBD is like a little better nationally, but still THC, it's more legal state by state, but there's still issues with the whole banking system. So there was a lot of thorns with actually making a successful business. And we did kind of, there, at the end of the day, we were able to raise some money. We had a good time with it. We were able, I was able to
you learned a lot.
Make a salary. I learned a lot. And, but eventually we were able to stick around for a few years, which is better than some businesses. But, like, what is it? 90% of businesses fail in like a year or 6 months or something. So
no, you guys...
we were live for a few months, and eventually it was kind of perfect timing. I ended up, getting back to physics, because originally I was like, oh, this academia thing isn't working out, so maybe I can just make a bunch of money and then do my own science. But then I'm like, what am I doing? I'm just failing at making money and not doing science.
Well, sometimes you need that. You need that break. You need that side. You need that side tangent. And I tell to the kids all the time, like, don't feel like you have to be on this track that you set for yourself forever. Like, you can take side quests and see, and the skills you learn from that side quest will help you get a fresh perspective when you come back. Yeah.
Now I'm doing all these data science type stuff. Like even for my job, like I just wrote a web scraper to interact with 11 labs. Like we're working with this guy who speaks Russian, and he has this device that he's tinkering in his lab, and no one can talk to him.
Yeah.
He has all these YouTube videos. So we had this engineer who's building, like he spent 3 days. He's trying to reproduce this thing in a lab, but he had to spend 3 days just converting, clicking the buttons, doing this and this. And I was like, look, I can just write a web scraper that injects the video file, automatically downloads it, puts it in a file, and does all this stuff. So now I just, it took me a day, 2 days to write that, but now
it saves him.
It's completely automated.
Exactly.
So now it's like, now just send it to me and I'll click this button. And I would have never learned that if it wasn't for that data science thing. And so another thing, just in terms of advice, like when you're going through your life, sometimes things so chaotic. I feel like you can never really predict what's going to happen in the future, but doors will open. You just don't close doors.
Keep knocking.
Try to keep doors open. And you never know, like, it kind of like when you're looking back on it 5 years later, it's gonna look like this elegant story as if you almost planned it, but you're gonna be.
It looks like chaos when you're in it. It's chaos when you're in it, but when you get out, you're like, oh man, that was great.
It becomes this elegant masterpiece that's a better piece of art than you could have planned, right? It's almost like this artist who's in the flow. You could just like plan it out and be like, I want to do this, I want to do that, or you could just. Some artists, they just go to it and they have these skills a little bit. They don't exactly have the plan, but then they do these things there, and then it comes out. And so it's just like, wow, how did you create this masterpiece, right? And it's like they can't even explain it, right? And I feel like my life in a certain way has been like that. So I've had a lot of rough times. It can be very discouraging, but just keep faith, like keep that long-term vision, and just don't give up. Never give up.
Never give up.
Don't quit.
I love that.
You're gonna have to do some tasks. Maybe what you have to do today isn't what you want to do, but have that discipline to know it's going to stack up. And once you do all those other things, or even, sometimes it's about not like, what do you do that everyone else hates that you don't mind doing? It's like, I don't like computer programming, to be honest, but if there's some task that needs to be done, it's a useful tool. And I don't mind doing it, where someone else might hate it, right? Or maybe there's something that's difficult, or just no one wants to do it, but it's like, hey, it's not like I love that, but it's useful to society and I don't mind doing it. There's a lot of opportunity and stuff like that.
Yeah, I would say I have this quote of like, you got to do the things that people don't want to do so that you can do the things that people later can't. Like, it'll put you ahead. Yeah. Nice. I like that.
Yeah, definitely.
That's a good piece of advice.
That's a good point.
And then he says, okay, last part of his question was yours. Do you believe that AI could be useful for college students, and why?
Definitely. Well, I mean, first of all, there's all the text-based.
There's all the write my essay for me.
Well, not that, but as a learning tool, it's a more. It's not. You shouldn't look at it as, oh, does it replace Google searches? It's just simply a different tool. Sometimes I want to get information, and I just kind of know. I've been playing with AI a lot, so I have a pro subscription to ChatGPT, and so all the time, like even sometimes it'll be like stuff that I should know, and I'm just like forgetting, like I just want to make sure I got it right. I'll just ask ChatGPT like, what's this topic? How does this thing work? Right? It's good for like validating things sometimes, but you can't blindly trust it all the time. But
yeah, you got to review
you can
it.
Follow its logic. Like sometimes you'll see the logic it's doing, and it'll kind of get the logic right, but then just at the end say something that's obviously wrong.
And
so you could just throw it away and be like, oh, the AI is useless. It didn't, I didn't know what it's talking about. But
got 95% of it.
It can be used. Yeah, sometimes you can I've even used it for research. People are still saying, oh, it's not good for scientific research, but it turned out there was this thing that was really subtle that was kind of, it was perceived in the physics community as being trivial in a way, but it turns out it's actually highly non-trivial, but it's like no one talks about it because to even write it up in a paper, it almost looks like kindergarten stuff.
Oh, okay.
But it turns out there's all these subtleties that no one's talking about. And so I had to figure this out for this project, and I asked ChatGPT to like figure it out, and it never got it right, but I saw the logic it was applying, and I was able to figure out how to do it a lot quicker than I would have otherwise. But also, just learning. I like sometimes I get into this habit where I feel almost dumb for using ChatGPT now, where I'm like, oh, it's like I could figure out for myself, or I'll just ask it and it'll tell me the answer. And I feel almost bad for
like you're
doing that, it's
cheating.
like, oh, I'm useless. Yeah. But then I'm thinking, I'm like, how is this any different than a search engine? At the end of the day, like, right? Like, I'm just asking Google, hey, what is this thing? It's just a shorter expression.
Yeah.
So, I mean, for more, like, the AI is good. The
tool.
large language models are good. When you have something that's like a little more complex that you can't, let's say you want to write a sentence or a paragraph. If you need like, if you want to debug something, you want to learn something, some concept, like explain this to me. Like it's getting a customized response. Like if you go to Google, it's not going to write a custom web page for your question.
Yeah, no, it's just going to try to find a page that's related to it. Yeah.
So if you kind of know, it's like, oh, if you're trying to do, let's say you're coding something and you're trying to create, you're trying to create like a snake game, you know?
Yeah.
I mean, like there's tons of people on the internet who have done that before. So you can Google it and be like, how do I create a snake game? Right. And you're going to find something, but maybe you're trying to combine 2 or 3 concepts.
Yeah, snake game with like Minesweeper or something.
You know, whatever it is, right? You're trying to learn, maybe it's some specific biology concept and it's almost too big to word in a Google search, right? Ask ChatGPT to explain it, right? You know, maybe you don't even need to add, hey, get it to do my homework. I mean, you could honestly learn from it as an educational experience, but, you know, also don't blindly trust it all the time. But, you know, honestly, it is pretty good at a lot of stuff. And I mean, now there's just all these other AI tools where I think what it's going to allow you to do is it's going to make it a lot easier to create your own business in a way where you could be a college student. People have done this where there's college students who have started their own business where they are writing ebooks, right? Where they're using ChatGPT to write books, and they sell them online.
They sell the books,
They're making money. I mean, it's kind of a cool thing. I mean,
these AI books are a huge thing. So one of these other streamers I was watching, his name's Paleontology, and he was reviewing these AI books, and they're like drawing books. So they're AI generated books on like, here's how to draw a dinosaur, and then he goes through it, and he's like, dude, this is absolutely garbage, dude. Like,
yeah, I mean, obviously you can generate a lot of crap, but. I mean, and I'm not saying you should do that now. I'm not saying, if you're in high school, wait 4 years and then go to college and then use AI to write books, because the market's going to be saturated.
Yeah.
But you're going to have to kind of learn. You're going to have to, it's like you kind of have to be ahead of the game, right? Like you don't want to like go in the store. Like I was actually helping this business out, and one of the issues was it was a really big company and they were selling products at CVS, and then they would try to sell their products, and then CVS was like, oh, well, actually, we just got this other product from another company. Like, and so then they're like, oh, we need to make that, right? But it's like, no, you're already too late. If it's already to market.
Yeah, if they're already talking about it, it's saturated.
You kind of have to kind of see the vision of what's coming next. What's like about to hit the market that's just barely not there yet. And because you're going to be young, so you're going to have to learn skills. So how do you become competitive? If someone's already done something for 5 years and it's already been done, like, how are you going to compete with them? But if something hasn't occurred yet, but it's about to happen in 6 months or 18 months,
being able to like see around the corner
now.
Yeah.
And you're like, other people, they won't be focusing on it. Maybe they had some skill that's adjacent that they've studied for 10 years and they have this talent, but you've been laser focused for 6 months where you can get in, and now maybe someone gets there first and there's one thing like it out there, but you do the second one, right? And it's not even that big of a deal, but it's like you got that edge, right? And you get it out there. I think there's going to be a lot of opportunities with AI where you can just be creative and try to predict what's going to come next. And how can you use these tools to solve problems that people are actually having in the real world? There might be something creative that you can come up with.
Yeah, well, that's super cool. I like that. It's enabling you to basically do the job of what, like, you know, a 10-person company is, you know.
And right. With all these tools, it's going to be that much easier to use AI to launch a business, right? Oh, I got to make a website. Well, now you can just
usually you'd have to
AI custom website, right?
Yeah.
Now I need to do social media. Well, now you could pay $50 a month.
You don't need to pay a copywriter anymore. You don't need to pay a developer. You don't need to pay this. Yeah, ChatGPT can just replace.
I mean, maybe this is more relatable with music, right? Maybe like kind of the whole DJ thing, or even self-promotion. Like back in the day, you used to get a record label. You know, you'd buy the CD, right? But now it's like you just put it on the internet, right? Anyone can do it. And then, you just get a microphone that's $100, and you get this other recording thing. like back in the day, you need to buy like $10,000
You needed a studio.
worth of
Yeah,
equipment.
you needed studio
this
time. You
expensive
needed all this
studio.
stuff. Yeah.
But now you can just be a guy in your bedroom with an acoustic guitar and a microphone and amplify, just put it out there and get millions of views. So AI is gonna do like that type of thing for arbitrary businesses.
Sure.
Especially, the digital world, on the internet where people are gonna be interacting, and it's gonna make it easier to scale. So it's gonna be a lot easier to be an entrepreneur by yourself. So it's going to change the traditional job market where, this was something where even my dad, like it was, he was kind of like, you got to get a job and do the traditional thing.
Sure.
And it's like, yeah, that is a route, but even the idea of remote working from home, like it just opens up opportunities where now you're going to be able to do things in ways where that weren't possible in the past. So really don't get discouraged about how fast things are changed. Like stay ahead of that and realize if you're young and things are changing quickly, that's better because AI is new for everyone.
It's flushing out the established people. It's allowing you to everyone now is on a level playing field because everyone's starting from scratch.
Everyone's starting from scratch. At the end of the day, you don't need to write AI code to use these LLMs, right? And sometimes it's a different skill. Sometimes if you are a programmer, maybe you kind of understand how they work, so you do know how to prompt it, but some people aren't. Like some of those nerds that are good at programming, it's just like, other people, they just don't know how it works at all, but they can use it effectively because they know how to communicate. So English, speaking, writing skills are still going to be more as important as ever because at the end of the day, it's communication with all these, at least with the large language models. And then it's,
you have to communicate
we'll see
in
when
English.
the robots start coming in and whatnot, and all that stuff. So, but so that's the type of thing. The large language models are like the big AI right now, but just keep an open mind about where it's going to go, where you think it's going to, you're going to go to school. Let's say you're going to go into college for 4 years.
Yeah.
Try to predict what's not going to come out for 4 years, but might come out in 5 years, right? If you have that vision to start planning, then you can kind of get an edge where other people wouldn't even look into it until it hits the market.
Exactly, but you've been looking at it.
You've already prepared because you kind of predicted, you had that foresight to see, well, it's obviously that is a challenge within itself, easier said than done, but, just keep an open-minded and don't get discouraged by all the change. Realize that because you're young, and when you're young, you also have the opportunity to take risks. You don't have a family.
Oh, yeah.
So
Yeah, the responsibilities
stars, try for something big.
Yeah.
And, if it doesn't work out, then you can, fall back on getting a job, that just pays the bills. But, you have that opportunity to try something big.
Yeah, go for it. YOLO it.
That's dope.
Nice. Okay, good. Let's go to the next question. Not Your Friend says, given your recent interest in the UFO and alternative propulsion community, do you see any theoretical connections or implications between your work in theoretical physics and the unexplained phenomena observed in these communities? How might your expertise shed light on the seemingly unconventional propulsion systems reported by some UFO sightings?
Yeah, so there's kind of 2 or 3 routes to this. So on the one hand, it doesn't seem like these devices are powered by oil.
Yeah.
So how is that happening?
Right. Yeah.
So what?
And they're not even fluid-like, right? Like the typical propulsion, right? Is using thrust as like a fluid, but I think what you've been researching is like things that don't even move like it's a fluid.
Yeah. So there's kind of like the true anti-gravity and then alternative propulsion, let's say, right? So there's kind of, like maybe I'm not going to make a UFO tomorrow, right? So, but there's some gravitational physics that I've been looking into. I mentioned torsion and non-metricity. That's what I'm banking on. So Eric Weinstein has gone on the record and he says, oh, what's going on? There was this conference in the 1950s where these aerospace people got some ROAS thing, or I forgot what it was called, some conference, and there was all these smart physicists. Basically, there was some rich guy who had a bunch of money who wanted to figure out anti-gravity. And they were talking about this non-Riemannian geometry, and that's how Eric refers to it. And what that is torsion and non-metricity. And he's like, what happened there? Why aren't people looking into it? It's like, well, have you read the literature? It's actually been an exploding field in the past 5 to 10 years. The number of papers that have been published on these they're not talking about anti-gravity, but just studying the hard mathematics of how it works. So I've been studying that, the gravitational theory, and I think about it and it's like, well, how could we experimentally detect this stuff? Honestly, it's gotten to a point where you're not going to just randomly come across, it's so weak, this stuff. These forms of gravitation, they're weird. They're like gravity is kind of an external force, right?
Yep.
It's like kind of out there, but there's these other gravitational forces that are internal, which is counterintuitive because we typically assume gravity is external because that's just what we know right now. And as I was saying with the spin density thing, like it seems that when they're smaller, usually gravity matters for big things, but for these types of gravity, it seems that smaller is actually more important because it turns out there's this ambiguity where if you look at it in a certain framework, you can actually get it where this curvature and torsion is actually the same thing. But it's like you stack up an infinite amount of torsion and it's the same thing as curvature. So there's this sense where torsion is like infinitesimal curvature. So to really like prove that it's there, it's almost like you need to go to a regime where there is no curvature and the only thing left is just a little bit of torsion. But then it's so small, it's hard to fathom how you could ever engineer something. But I don't know if these UFO are out there and they are doing things to warp space-time. There's this idea, it's called metric engineering, how you can engineer the properties of space-time to bend at your will to get warp drive, right?
Yeah, these are the warp drives.
My thought is like, if you want to metric engineer, you really want to like go in with a soldering iron and be able to add or remove a single point from space-time. Whereas the curvature is kind of taking out this wedge.
Mm-hmm.
It's called a wedge disclination. There's a buzzword.
A wedge disclination.
So there's also so that's the curvature in general relativity. It's described in that way, or you could have this line defect that's associated with torsion, but then a line is just an infinite number of points. So I'm studying how to add or remove, theoretically, how to add or remove a point from space-time. And I also think that this might be related to electric charge, whereas the spin density stuff is these types of line defects related to torsion. And so there's something going on with rotating charged objects.
Yeah, because we always think of like the flying saucer,
states.
right? We always think it's a flying saucer, like it's rotating.
Yeah,
right?
Because there was some Germans, Maria Orsic, in the 1920s or so. She was a part of this society, the Vril Society. She started channeling.
She looks like a Barbie
information.
doll. Who's this person, dude? What?
Yeah, so she was a medium or a psychic who wrote down engineering specs for a craft, and that led
for
to
Hitler,
the Germans. yeah. So
what?
Legend has it. I mean, they found some of these UFOs and they started putting weapons on them, but they didn't ever get to the point where they could. It was like far enough along where they could use them in the war.
Oh my God! What the Nazis were creating flying saucers, dude? What?
Yeah, and so there's something about rotating discs. I mean, literally, the thing that I'm working on right now, it has 3 discs. One's rotating one direction, the other is rotating the other direction, and
conservation angular momentum, right?
Is not rotating, and then they put it to a high voltage on these 2 things.
Sure.
And then they hook up a Tesla coil in the middle one. It's like, what? And we found the inventor was studying stuff from Victor Schauberger, and there's actually a picture of one of these devices that was 3 discs and they were rotating, and so there's something going on.
Is it like this? Is this thing? Where is it? Victor Schauberger?
It's not the exact picture I have in mind, but yeah, it's gonna be hard to find it with. I'm trying to think of how to. Trying to remember the name of the device. I mean,
this thing looks pretty cool. This looks pretty cool.
Yeah. So, I mean, something happened in Antarctica in 1947 as well. That's another wild one.
Yeah, that's another. Yeah, I remember you talking about the Nazis in Antarctica.
I mean, yeah. Why are there Nazis in Argentina, or why are there like Germans in Argentina?
Yeah. Yeah. Why they go to South America?
Because it's close to the South Pole.
Yeah.
But
what
anyways,
are they doing?
So, trying to get back to the questions. Yeah. So that's one example of how the gravitation that I'm studying, I believe, could relate to that. And it's at the point where I think the only way possible to detect these subtle forms of gravitation is you have to be crazy enough to assume it's real and try to engineer it. Mm-hmm. Like, you have to be really dedicated. You're not just going to stumble upon this in the laboratory accidentally. It's so subtle that you have to really search for it. And so I also have some electromagnetic insights as well. It's a little technical, but yeah, basically going into deep history of electromagnetism and revisiting things, I think those might also be relevant. So, and then understanding how the electromagnetism interplays with the gravity. Maybe you don't literally need a whole unified theory, but it certainly would. I mean, at the end of the day, I think the point is how do you use electromagnetic devices to create these gravitational effects? So if you only have electromagnetic theory, it's not going to contain those gravitational effects. So I'm kind of breaking it down where my strategy is to first, don't even worry about anti-gravity. How do you make a device that flies with electromagnetism?
Yeah.
Get that down. Then maybe you actually are studying that, and when you get up the power high enough, maybe it turns out you could start realizing maybe there's some gravitational things going on as well there. So it'll be a work in a progress. Obviously, it's a challenge.
Because you got approached, right, by
topic.
this anti-gravity kind of UFO company. Why did they select you? Why did they pick you?
Well, yeah. So there's a little bit of a history here. So what happened was, actually, it started with this this email thread. There's this guy Jack Sarfati who's a character.
Okay, I like characters.
Within itself, he's kind of like the Trump of physics. So he's super crass. He's super rude. He sends out these emails. He's always blasting people and just, oh, you're an idiot. Oh, you don't know what you're talking about. But he's kind of smart, but he's almost like, he's kind of like one of those armchair, too smart for his, he's always using these fancy, like, he's kind of crazy at the same time. Like, he does know something.
Dude, this guy looks like Nostradamus.
He claims to be the inspiration for Doc Brown. So,
oh, really?
Back to the Future.
Wow. Yeah.
He claims that he is that scientist, basically, because he was written about in this book called "The Hippies Who Saved Physics" or something like that.
Okay.
And so, he actually, it's strange. I mean, he got a PhD. He kind of moved out to, I think, he went to UCSD, and then somehow like got a job working. Well, actually, I missed the crazy part. So when he was 13, he got a phone call from, I don't know, some robotic voice that said, "We are you from the future.
Oh, God.
You need to go talk to someone in the military and join this program."
Yeah.
And so he bought it hook, line, and sinker, and was like, oh, there's like, I've been chosen for this special program from these people in the future to like join this, special program or whatever when he's 13. And it's like kind of a crazy story.
He says he got a phone call from an alien. Yeah, it says a phone call from an alien, dude.
Well, it wasn't an alien. It was a robot. Like, it was almost like an AI, from the future in the 1960s or something, maybe the 50s. I forget the exact year. And so
a conscious computer aboard a spacecraft is what it says. I'm from the future.
Okay, yeah. So it's like, is it a spacecraft? Who created that spacecraft? Is it aliens or is it us from the future? I don't know. And so, but it was definitely from the future was the idea. So he's, and basically, so eventually by the time he got his PhD, he somehow got paid by these kind of black budget, sort of CIA adjacent, I don't know, things to kind of figure out how does consciousness work? What, kind of looking into all this crazy stuff and UFOs. Yeah. And so he was kind of like the UFO physicist. So then obviously, in certain, in academia, he has no reputation. If you even, here's the other one. If you Google torsion field, I think there's a Wikipedia page. Okay. For it.
They call it pseudoscience. Yeah. What? They don't believe it's real.
And so, just Control F, you can find Jack Sarfati mentioned on the page. And so the ironic part is, torsion is in string theory.
Oh, okay. But they say it's a pseudoscience.
Torsion was created by the mathematician named Elie Cartan, who classified all of the Lie algebras, which leads to all of the symmetry groups. That is the foundation of all modern physics. So, how is it pseudoscience? It's literally in string theory.
I know. I think it's the marketing technique, right? Because they're saying that they claim it has homeopathic cures, telepathy, telekinesis, levitation. These are words, right, that like instantly turn off like this. Yeah, I mean, levitation is real.
How UFOs work, right? Like,
I know, right?
I mean, what are they doing? I don't like. So yeah, I mean, it's controversial, but now that more and more stuff is being seen, the perception is starting to change. Where now scientists are like, well, I don't know how these UFOs are working, but maybe there's something there. I mean, these pilots are saying they're seeing things. So yeah. Anyway, so how I got into this was I somehow well, from my last job, my boss there knew Jack, and we just he started sending out all these emails.
Clee knows Jack. Clee and Jack, they would know each other, right? Yeah,
so
they're
they
like
knew
peas
each
in a
other.
pod. Yeah.
And so then basically I had gone to Italy to visit a collaborator, Alessio.
Okay.
And Jack happened to be giving a talk in Italy.
No way.
At the same time. So Mike and I went to the conference, and there was like, who's going to fly out to Italy just to
listen to this quote unquote like crackpot person. Yeah.
Right? It's like, who's going to realistically fly out there? So, I mean, there was like 2 other people. Well, there was like a local school, like a local high school had people come, and then like we got there. So he was like, wow, like you actually came, like, so.
Yeah. You're like, yeah, we flew here all the way for you, dude.
So Jack kind of always craps on everyone. He's like, everyone's an idiot. And so what happened was there was this APEC community, and they have all these wild talks, but they're trying to figure out propulsion. They're more like engineers and kind of tinkerers or whatever.
Okay.
And they're trying to figure out how these things work. And so they were trying to get Jack to give a talk.
Mm-hmm.
But Jack was like, no, you guys are crazy. I don't want to associate myself with you, blah, blah, blah. So then they were like, wow, I mean, Jack is saying that this David Chester is actually like kind of smart. Like he never says that about anyone, like he's always hating on anyone. So then I just gave a talk to that community, and so then they, just because usually they had a lot of oddballs,
Yeah.
So that's kind of how it all started. I mean, I wasn't really even, I'm kind of open-minded. I'll look into anything, but it's not like I was like, oh, I need to figure out how UFOs work. It just kind of happened, and then it was like, well, I mean, this is getting more popular, so maybe I should lean into it, because once again, it's like you see this coming, right? You see it coming where it's like there's going to be a day where scientists are going to study this. So I have this opportunity to kind of get in where I still don't know how they work, but if I just put myself out there now, it's like what physicist in academia is willing to touch it, right?
Yeah,
but
right.
Now it's like, and then, next thing I know, it's like I'm getting asked to join this podcast and get flown out to Florida. And they're
it's the concrete one. You're the expert on UFOs, yeah.
I don't know that much, like, really, but it's so it's a little bit of marketing, right? I was able to kind of figure out the right way to market it. And yeah, I mean, at the end of the day, it was kind of funny in that talk that I gave. They were like, hey, can you just not talk about the math? Like, we have a bunch of engineers.
Yeah.
I was like, well, okay. My first slide was, what does an engineer do? Like, what does a mechanical engineer do? A mechanical engineer learns Newtonian physics. They learn mechanics. They learn more than the physicist. They learn about stress and strain and elasticity because they need a building to not fall down.
Yeah.
They learn more classical mechanics than I learn.
Right.
They're an engineer. They learn more of that type of physics. What about an electrical engineer?
Yeah.
An electrical engineer has to learn about electromagnetism.
Yeah.
What about an aerospace engineer?
Yeah.
An aerospace engineer has to learn mechanical,
Fluids.
electrical, fluid dynamics, thermodynamics. They need to learn everything because they're trying to make something fly.
Yeah.
So if you're trying to make a UFO,
you need the math.
warping space-time, you're going to need to learn general relativity. So it's like, next slide, here's general relativity. Like, oh, no, like, I don't want to learn all this math. But,
it's like, but you have to.
Break it down. But, I mean, hey, like, if you're going to take this seriously, you're not going to just tinker, because the problem with this stuff is...
Well, everyone's looking for, like, a fast solution. They want, like, some, like, cool, like, unique thing that just pops up, and they're like, oh, here, we got it. It's like, no, dog.
So they have this Alcubierre warp drive, but you need negative energy, which... Like,
negative energy?
What
the fuck is negative energy?
Right. And you need a lot of it. Basically, Einstein's field equation says matter sources curvature, but the coupling between the two, you get this factor. It's it's 8 pi, and then you got a g, the big G, and the c to the 4th in the denominator. Yeah. And so that coupling is very, very small. It's like 10 to the, I think, minus 43 or something like that. So you need, just to even create a gravitational influence, you need a lot of matter, right? I mean, we know that for the Earth is huge, and we fall back down onto the Earth. But if we high five each other, we don't feel the electromagnetism more than the gravity.
Exactly.
So you're not just gonna tinker your way over 43 orders of magnitude. You know, like, yeah, like you could get a factor of 2. You know.
Yeah, we get factor 2.
I'm talking 10 to the. That's 10. And then 42 more zeros. Like, you can't even fit that on a single line.
No.
You're not just going to randomly stumble that over that engineering in a lab. You're going to need to know that theory. That's kind of my hypothesis. I mean, you know, that's why no one's studying, because it's so impractical to imagine how you could possibly do it. But that's the thing. If there are UFOs out there, if it's real, and even better, I mean,
start studying it now. Yeah, this is what you've been talking.
Have already reversed engineered this technology and it's being siloed, then that means humans can do it, you know?
Yeah.
And so it's only a matter of time. I mean, who knows if that's actually true? I don't know, you know, but that's what I think. But, you know, it's going to be a time where it'll be doable. So someone's got to do it, I guess.
David Chester's the guy for the job. Nice. Let's see. Next question. Taco Cat. Did you ever think you would work in this when you were ever a young kid? Who inspired you to go through this path? What was your favorite study that you worked on? What was your hardest study? What study would you want to work on right now? Maybe pick a couple of these questions. Do you study dark matter?
Yeah.
We kind of went over this. And then...
Yeah, so I mean, we talked about some of these. I mean, honestly, when I was a kid, I had no idea what I wanted to be. Like I was saying, it was like, oh, I'm good at math. People say I should be an engineer. I literally didn't even know what that meant. And I was like, I don't know, I guess I want to be an engineer. And it wasn't until late high school. But even when I finished high school, I still didn't know what I wanted to do. I was thinking physics, computer science, or electrical engineering. Even when I was a freshman, I still didn't exactly know. By the end of freshman year, I was kind of like, okay, I think I want to be a physics major. And it was simply because, I mean, at that point I was at MIT, so I just figured if I want to get the best job possible, I should go into computer science. But I think I didn't really care about money. Like, I wanted to be able to provide for a family, but I wasn't like trying to.
We can hear your family right now. Is Clover okay?
Yeah. She's crying. Babies do that. Sometimes.
Babies do cry. Yeah. So, anyways, computer science was maybe a thing, but then you were like, I
just started looking at the classes, and it was like, for computer science, I would enjoy half of the classes. Then others, I was like, But the physics, it was like almost all of the classes I was excited to take. So I figured, why not? I could go in that direction, and hopefully I'll be able to get a job. Yeah. And so, that's kind of what I did. And it really was, once I realized that once I applied myself, and I could still, it's almost like, for whatever reason, for me, like, I'm not good at perfecting simple things.
Sure.
But when things get harder, it's almost like I always get a 70%, you know?
Yeah.
And when it gets, you know, or like in between 60 and 80%, like if it's super easy, like maybe I'll still make a little error. But when things get really difficult, rather than just like completely failing, I'll still do mediocre. And so it was until like college that I realized that. And because I was one of the few people that I even knew that I got better grades at college than I did in high school at MIT, because most people were straight A students, and then they go to this really hard school, and it gets harder.
Right. Big fish, small pond.
And I mean, this is another point of inspiration. Like, I wasn't motivated from a young age. Like, I had this spark once I went to college that I didn't have in high school. So it can develop later where, you know, I just didn't care at all. And then all of a sudden it was like, wait a second, I could actually do something that would actually be, you know, I was actually good at it. And then that kind of, once I realized I was good at it, like at a higher level than I realized, then that made it easier.
Yeah.
And so, I have studied dark matter a little bit, but that's not really my expertise. Honestly, my undergraduate thesis project was extremely difficult because I had to learn a new programming language, C++, and I had all the memory allocation, but not that. I had to tie it in to this software program that the lab had developed over a decade. And so I would write code in this language that I don't really know how to use, using their package, and then it would error out. And it would be like, there's an error in this file, which is calling this file, which is calling this file, which is called this. It would be like 7 files deep.
Oh, no.
And I've never opened
the
any
worst
of these
debugging
files before.
Yeah.
And I don't even know, like, I barely understand how this programming language works. So, honestly,
your senior thesis was a mess. Like, yeah. Mine wasn't that bad.
Undergraduate thesis, it was so hard for me. I mean, I spent a year or more, like, just trying to, like, do the thing. Like, it got to the point, it was so embarrassing. Like, my advisor just kind of, he banged it out in this other programming language that's easier to use that didn't use the software. But he, like, banged it out in, like, a week. He was like,
he's like, yo, here it is.
What are you doing? Like,
yeah.
And he's like, you know, does it work? Like, all right, but it's like, yeah, but like I had to use it. So that was like when I got my first panic attack, because it was just like I had never felt something like that, and I just left my desk.
For me, it was quantum, dude. Quantum was my first panic attack when I just couldn't get what was this Goop Pearl was saying, dude. I just did not get quantum, dog.
Oh man,
that was my first oh fuck, I'm stupid.
I didn't think he was an amazing teacher either.
Yeah, he wasn't the best teacher,
but
he's a smart guy.
You know, you do what you can. Yeah, he was smart. Yeah.
Do you think we can discover wormholes?
We could discover the fourth dimension.
Well, we have the fourth
dimension is time, so I think we have clocks.
Yes, we
so
do.
That's
clocks.
good.
I've watched
the wormholes in 5 decades, or that's an interesting question.
Do we have evidence of wormholes, or is it just a theoretical conjecture?
It's just theoretical, but even Juan Maldacena, who is one of the top physicists at Princeton, came out with a paper maybe a year or two ago talking about traversable wormholes.
Okay.
I looked into it and it was like maybe they could get like a half of a hydrogen atom through that wormhole.
Okay.
But it was also in this 5-dimensional theory of gravity.
Okay.
So we don't know if that's the right theory either.
So wormhole is basically like a bridge. It's a bridge between space-time, kind of like a like this folded animation here, right?
So it's exactly like that. So it's almost like
it's like a shortcut.
A shortcut, right? But here's the thing: if I can add and remove a point from space-time,
yes,
and then construct a bridge between it, I mean, I feel like I see some mathematics that people are missing, but I wouldn't say 50 years. I would bet it's going to take longer than 50 years.
Mm-hmm.
Maybe 100 to 200. I could imagine that occurring. I would say 100, 150 years, maybe. It could also be 1,000 years. It could also be 10,000 years. It's really hard to tell.
Orders of magnitude, we don't know.
I mean, it does seem like the population of humanity will level out. Like, we're not going to just keep expanding. I mean, logistic growth, it's exponential at first, but eventually, it does seem like
it's a predator-prey model. Eventually, we're out of resources.
We don't really know how it's going to turn out. So, I mean, with the advance, it could, some people think it's going to be some doomsday thing where we just run out of resources and then everything, and it becomes like some Mad Max, whatever.
They call it the heat death,
that's
right?
Going to happen.
The heat death.
The heat death is.
Oh, that's something else. Yeah.
That's like billions of years. That's like.
Yeah. That's the end of our existence.
That's not our concern.
Yeah.
Well, yeah, but that's like the universe dying, and that's also like a classical thermodynamics. That's like so antiquated, anyways. That's an 1800s perspective.
Oh, really? Oh,
but yeah, I mean,
old news.
I don't really believe in the heat death thing.
Doesn't believe in the heat death. Not real.
Yeah. I mean, that's actually a misconception of entropy itself at a deep level.
You have a lot of cool theories on like, was it the second law of thermodynamics? I think that was the original stuff you were saying, right? That was like kind of controversial, right, in physics.
Yeah, because
perpetual Mabon machines and stuff.
What I realized what happened was, I could go to a professor and ask him what would happen in this experiment, and I could pitch it in 2 different ways. And depending on how I explained it, I could get them to tell me whatever answer they want. And both times they would always say it's just like trivial 1800s physics that everyone understands. But it's like, depending on how I asked it, I could get there was no consensus.
Was this your poking the bear? Your poking the bear like technique where you're just like, ooh, I can poke.
And so there was this old emeritus professor who was like, let's do this experiment. And it's so simple. It's related to, why does it get cold when you climb a mountain? It's literally that simple. I mean, when you look into the atmospheric scientists, the equation, and the equation they use of why it gets colder is what I was saying. There's a way where you can actually, if that's true, and you can create a perfectly thermally insulated device, and you make 2 of them, and you make them have different types of thermal materials in them so they conduct heat differently, and you thermally couple them at the bottom. They'll reach thermal equilibrium at the bottom, and since there's gravity, you'll get a different temperature in the 2 columns at the top, and you can use that temperature difference to power a TPV system.
It's a heat engine, right?
The heat engine, right? Heat flows from hot to cold, and you can take a fraction of that thermal energy and use it for work. And this was proposed as a thought experiment to
what's the name of this thing?
James Clerk Maxwell. Well, there's not even a good name for it. You could call it the Low-Schmidt paradox. When you Google the Low-Schmidt paradox, you're going to find something else. Low-Schmidt had like 5 or 6 different paradoxes. And
Okay.
the one I'm talking about is a very specific one that there's not really that much good information. It's hard to
I
find.
was just trying to see if there's like a picture of it or something now.
Yeah, it's pretty obscure. But I was into that, and I was just like, look, we need to understand how this works. It's so simple.
Yeah, Sensation says, where's the energy come from? It comes from the ether, right? You see, the energy comes from the ether? Or
no.
Right?
I mean, this had nothing to do with that. This is literally just heat flow. And so the idea is, okay, a little energy goes across, and then you disconnect the circuit, and you wait enough time, and things will re-equilibrate to their steady state solution.
Yeah.
And so Maxwell himself said, oh no, I don't think there will be a temperature gradient.
Oh, okay.
I think it's because that would violate this. Like, if you could just do this thing and keep extracting energy forever. So I actually proved that it doesn't last forever.
Oh.
And it's not a perpetual mobile is something that lasts forever.
Yeah.
Eventually you extract all the heat out of the system and it gets to 0 Kelvin and you're done.
Yeah,
So
yeah, because eventually you run out of temperature. Right.
But they never thought of that. So I proved that it's not a perpetual mobile, but I never published that because I was trying to do an experiment and I didn't basically.
This isn't the big disc I helped you move at some point. Was this the big disc I helped you move?
Yeah, it was that thing.
Oh, was that thing?
That
oh, man, dude. I think it's massive, bro.
So my advisor told me, I came to him, before he was my advisor, I came to him paperwork. I was like, you need to sign this to be my advisor. And he told me, I'll only be your advisor unless you stop doing that experiment.
Oh, wow.
Which
he gave you an ultimatum? That's fucked up.
I took like 5 seconds as like, there's a lot of wrong ways to, bring this conversation, right? I said, okay, I won't do that, but I said, I moved to Los Angeles to study physics. I said, you haven't given me a project to do.
Yeah.
So as soon as you give me a project, I'll stop doing the experiment. But I'm not going to have me stop doing physics because that's why I moved up here.
Yeah, dude, what?
And he angrily signed it because he knew ethically he had nothing to say. Like, it's like,
why did he not want you to do it? Because you made him look bad or something?
It's too controversial. It's too It sounds crazy, right? And that was the thing. It was like, oh, he's trying to prove free energy. And I was like, I literally proved that it's not a free energy. Like, I proved it's not. It's just an extremely terrible thermogravitic battery. Like, it's extremely inefficient. Like, it's not useful for anything.
Sure.
But oh well. Yeah.
So. And they said, last question: who are the most famous people you've met in your studies? The most famous people.
Well, I walked up to Roger Penrose and asked him a question in person.
Oh, that's dope.
Once.
Penrose is very cool.
Nima Arkani Hamed is another one. He's
I know Nima. Yeah, Nima. What's his name? Oh, man.
Yeah. So I actually I asked him why he didn't cite someone's thesis.
Is this guy at Princeton, Nima?
Yeah. So he's really cool. He's a great scientist.
Yeah.
But yeah, there's a little drama because honestly, there was this lady who she's dead now, and she put out this work, but she was also like putting it on this blog.
Wait, is this the hiking woman?
Yeah.
You know what I'm talking about?
So
What's her name? What's her name again? Sorry?
Marnie Shepard.
Yes, Marnie. She just went missing because she was like.
Yeah,
like
she
hiking.
went on an extreme hiking trip and never was found. None of those are. Yeah, I don't know.
Yeah, I know.
It's
I know
double P, by the way. But anyways, so yeah, it was wild. So I just randomly met her at this conference, and I didn't know who she was, and then she was like, "Yeah, I've been suppressed, blah blah blah," and it turned into this whole like male conspiracy. And then, so it was kind of weird because I looked into her thesis, and she did talk about this topic. But it's just like she was kind of. So then I asked him. I was like, because she had lunch with Nima.
Okay.
What happened was, she mentioned this topic called associahedra. It's just this math buzzword, and then it turned out. So Nima ended up publishing a paper that was kind of related to those geometric things. And so I asked Nima. I was like, "Hey, did you?" First, I was like, "Did you have lunch with Marnie?" He's like, "Oh yeah, like I did have lunch with her," and I was like. Oh, okay. So why didn't you cite her thesis? And he said, it's vague. And I was like, okay, fair enough. Like I could see where he was coming from, because
Sure.
it was, I mean, she was like on the right track, but not exactly, you know, and she did have the right math. And so it was like she was too early, where everyone was
She was like
"You're
ahead of her
crazy. This
time. She
doesn't
was ahead
make
of her
any
time.
sense." Yeah. And she sort of saw a glimpse of it, but didn't perfect it. And so then Nima published, but what happened was literally he met with another mathematician the same day who was more reputable, and he mentioned Stashev polytopes. It turns out that associahedra are the same thing as Stashev polytopes, but he didn't even know that. Nima himself was learning this mathematics, so he literally heard about the same mathematics from two different people on the same day.
But he cited the one that was more reputable than citing her.
He had became a co-author. He ended up becoming a co-author with that other mathematician who
really?
happened to be a male, you know?
Oh,
so it's
there
like, you know, and also it's like that mathematician had published papers on this topic before. So it's,
sure.
Yeah, it's like he was the expert as well. And so, I mean, it's like, yeah, I mean, maybe he could have cited, maybe he should have, but
this is the modern day Rosalind Franklin, you know, where she
I
quote
don't consider
unquote
it plagiarism.
Yeah.
I mean, it's like, yeah, it would have been nice if he cited her, but he didn't have to. I mean, a lot worse things have happened before. I mean,
for
there's
sure.
tons of examples of flat out borderline plagiarism. I wouldn't even consider that. So yeah, I did meet him, and then it got weird where one of his guys was trying to box me out of the conference. I was like, God damn, all the politics. Yeah. So I don't know. Those are the two examples I can think of right now.
Monkey says, have you met Neil deGrasse Tyson? He's a big
I have not. I have not. Yeah. So I mean, he's kind of in the pop physics culture. I mean,
pop physics. Yeah.
You know, he's you know, kind of a spokesperson who is a physicist but I've never I'm also not really into astrophysics either. So
yeah,
I've never read any of his research papers. I see myself as kind of a physicist almost.
He's I'm a man's man. I'm a physicist. Yeah.
I don't know. I like looking into all the obscure topics that the mainstream misses and going to the underbelly of all the deep stuff. That's just, I don't know. That's just my personal interest. So, but yeah, I mean, he's a cool guy. He's obviously a great communicator. Yeah,
he's a good advocate. You know, I always say some people give him shit, be like, oh, he's not a real physicist or blah, blah, blah. I'm like, I don't care. He's putting that out. Any press is good press. You know,
does he have to be? I mean,
no, he needs to be able to just relate it to the general public.
One time I was talking to my advisor, because he was my advisor was skeptical of string theory, but kind of would dabble a little bit in some of this stuff. And I was talking about how it's so frustrating. I'm like, these string theorists, they're just doing all this stuff that's not useful. They should do this. And then he just said to me, it's why is a poet a poet? You know, and it pissed me off at first. It's what are you talking about? What does poetry have to do with physics? You know? But it took me 2 years to even get what he was saying. It was you know, at the end of the day, people can do whatever they want. You know, you have free will. If someone wants to write poetry, do it. If someone wants to communicate, if someone does science and wants to communicate about it and that's what they're good at, let them do that, you know? And I mean, I think that is a big problem, especially with string theorists, especially with particle physicists in general. They're terrible at communicating their ideas.
Yeah, they have great ideas, but they can't explain it to anyone.
To the public. They can't explain it to anyone, and that's why there become funding issues. And so, you know, at the end of the day, you could hate on Neil deGrasse Tyson, but to be honest, we need more people like him to help bridge the gap between conveying that information to the public.
No, I agree totally. Yeah, I say it's a lot when whenever there's these new. I always see this on the news where they're fusion breakthrough, and I roll my eyes because I'm this is not a breakthrough.
So cringeworthy.
It's cringe, right? But at the end of the day, I have to check my ego and be you know what? I don't give a fuck because I'm glad that it's in the news because now the public is learning about fusion.
It gets them excited about it.
It does. It's buzzwords. It's cringe. It's not real, but it gets exposure.
And there is something about it's even some string theorists I've heard where they're or another guy who was trying to hate on string theory and then put out a theory that looked a lot like string theory. And I was well, are you ripping them off or not? But it was he was presenting and the introducing me. He's well, we don't know if his work's good or not, but he's really good at inspiring the youth, which is important, right? Because he was like this guy. He would pick all these interesting topics. He's super energetic.
Yeah.
He's like communicating well, and like everyone's like, "What do you think is working?" Just like, I don't know, but he inspires the youth, and there's definitely value in that.
Yeah, gotta get people involved. Nice, good question there, Taco Cat. I like that. Was a good one. Jamarcus says, "What does the research process for something like quantum gravity look like? What are some of the experiments? Have you made any discoveries? What is the most shocking or cool result you've gotten from an experiment?"
Yeah, I mean, so overall, at this point, physics is sort of siloed in between theory and physics. So, I mean, even for quantum gravity, I mean, no one's doing any quantum gravity experiments. So,
I think we saw your notebook, like your research, right, is just writing things down on pen and paper.
A lot of times, yeah. And honestly, my whole position is that I'm not even doing that much quantum gravity yet. Well, I am working on one project that is literally about quantum gravity, but for the most part, my whole point is we need to understand the classical geometry at a deeper level so we can quantize it, and I think that will help clean up the infinity problems. And there's motivation literature, so I've been reading some of those papers, and so I'm actually a lot of the research I'm doing is more the classical gravity stuff, but then I'm studying these new quantization procedures that I think would be helpful for that. And then in terms of experiments, right? Like there was this thermodynamics experiment. Like I haven't done many experiments, so
yeah, you're a theorist. I'm the experimentalist, right? We went to grad school. I did experimental plasma. You did theoretical gravity stuff.
Yeah.
Right?
So I mean, my PhD advisor doesn't do experiments.
Yeah.
So and he literally, like I was saying, he literally told me to stop doing an experiment. So that experiment, I was trying to simulate gravity by spinning a rod really fast. So you get that centrifugal force, and so that centripetal acceleration is it's like effectively like gravity in a sense, but because the equivalence principle, you can't tell the difference between acceleration and gravity. So I was trying to take a rod and have it thermally isolated, and I put thermistors down the rod.
Oh, yes, I think I remember hearing about this one. Yeah.
And it would spin really fast, and I was trying to measure, and then we had a gas. We just put air inside.
Yes.
And we put this whole thing in a vacuum.
You see if there was a gradient, right?
And I wanted to see if there would be a temperature gradient. So that was one experiment. Now I'm more evaluating experiments that other people are doing. So there's this one device that is extremely difficult to tune properly, but it's basically this.
What's it called?
It's called the Graviflyer.
Graviflyer, dude? What? That sounds dope.
So it's got 3 discs. They're connected.
Is this it?
Yeah. So that thing is flying, apparently, and so it's charged to high voltage DC on the top and bottom, and then it's rotating. So they have these fan motors rotating those discs, and then they have a Tesla coil hooked up to the middle disc, and then they have an ultrasound unit at the top right there. He's pointing at it.
Yeah. Okay.
Pulsing ultrasound down, and then the bottom also has 6 magnets connected to the bottom disc that's rotating. And then it's creating some bizarre resonance state. The frequencies that they drive the AC at, the frequencies of
this guy's lab, dude. I love this guy's lab.
So right now it's my job to try to figure out how that device works. So that's it's not an experiment I'm doing, but I'm working with people who are trying to replicate that.
That's pretty cool.
That's pretty cool. That's one example.
The Graviflyer, dude.
Yeah.
What are the things actually like?
Yeah, so and honestly, when you look into it, it looks like a hoax. I mean, it looks super sketchy, but they've been in contact with the inventor, and they've gotten him on a Skype where, they asked him, all these questions, and he was able to kind of good answers. And so the team I'm working for is excited for the possibilities of it working. So we're trying to figure it out.
That's cool, dude. Yeah, I guess discoveries, most shocking or cool result you've gotten from an experiment?
Well, okay, in terms of discoveries, yeah, I mean, so I do feel like I have figured out a candidate unified field theory that I have submitted to a journal right now. And so it's unfortunate that Archive rejected it because the political landscape because it's kind of a taboo topic.
Yeah.
But it's right in between Garrett Lisi's E8 and string theory. So there was this mathematician who did this thing, and I realized that he didn't even think it was that important, but I thought it was really important, basically to turn E8 into a superalgebra, and the superalgebra is what's studying the string theory. And so it ends up relating to 12 plus 4 dimensions, and what I really figured out was how the extra time dimensions, it's not exotic, it's not as crazy as it sounds. It actually allows for mass flavor oscillations. So there's like the electron, and then the muon, and then the tau. They all have the same charge. They have the same exact like charge identity, but they have different masses, and no one understands the origin of those different masses. And so I put out a mechanism in which the extra dimensions efficiently encode those
what the differences are,
oscillations. And I mean, it doesn't predict the mass values, but what it does is it allows for the 3 generations to fit in this E8 algebra, because that was one of the problems with Garrett Lisi's work. So that's probably like the most notable thing. And then figuring out that like dark matter candidate, that was just kind of fun, because I like basically had a week to publish it and submit it, and like within 3 days, to my surprise, I actually kind of figured something out there. And then there's some kind of mind-blowing gravity stuff that I'm working on that isn't published yet. I just I did actually just get a paper that will be published that's on the archive that was about a new type of quantization method.
Okay.
And it was just remarkable to me that it hadn't been discovered yet. It's so simple and so obvious in hindsight that it was just really surprising. Basically, I went back to these 2 really obscure formalisms from the 1930s. And
is it this one, the 3 Fibonacci chain aperiodic algebra?
No, keep scrolling down. Let's see. Oh, you might need to. Let's see.
It says.
Oh yeah, click all paper. No, actually scroll down, because I think I almost saw it.
Monstrous M theory.
No, go up and scroll and click all papers. There's probably like a little. Under the showing 1 to 7, there's probably like a smaller text where one of those is like, it might be looking in underneath.
Oh, I see. Because it was only looking in math. Okay.
Oh yeah. That top one then, quantization of a new.
This is it.
So that was, honestly, the cooler stuff is in the appendices. But yeah, I mean, I combined these 2 different obscure formulations to figure out the right way to interpret this certain quantization procedure that allows for a more apples to apples comparison. So typically they say that quantum mechanics has a complex wave function. And so they kind of say that's unique to quantum mechanics. But it turns out there's this Koopman-von Neumann formulation of classical mechanics where you can have a complex wave function for classical mechanics.
Okay.
And it's really obscure. I mean, von Neumann's, a famous mathematical physicist. And so he's very famous, but this work was really overlooked. There's only like a handful of papers discussing it. And then there was this other de van der Waal Hamiltonian, I don't know. There's like Lagrangian and Hamiltonian.
Oh, I see. Yeah, all the appendix stuff you have here.
And so I was really trying to combine those 2, and then realized that basically there's a way to generalize that Koopman-von Neumann mechanics to classical field theory, so you can quantize it. And it makes it so the mathematics in the classical theory and the quantum theory is identical, and so it really isolates what the true aspect of the quantumness is, because a lot of times in literature they're like, oh well, classical mechanics we use this math, and quantum mechanics we use that math, and it's different because they have different math. And it's like, no, that's not really it.
Math is math.
Use the math on both sides. So it was really isolating what is the physics that goes into it, and so it's just surprising to me that it hadn't been discovered yet. So that was kind of cool.
Nice.
Yeah.
All right, good. Let's go to the next question. Ethan, how did Isaac Newton find the information for forces like his 3 laws of motion? Oh, it's kind of a funny question. Do you know much history about Isaac Newton? I don't know. I don't really know.
I mean, I know a lot more about the electromagnetism, but I've never read his.
What's it, Principia? Is that his thing? Principia?
Yeah, I've never read it. But yeah, I mean, I think there was a lot of people taking a lot of astrophysical data. There were, people stargazing, watching planets, trying to track how things moved. So they did have some data on that, and they understood that things fell to the ground, right?
Right, that's the whole apple, right?
So-
There was an apple in the tree and it hits him on the head, and he's like, like gravity.
Yeah, so it's like not clear if that story's true or not, but yeah, I mean, we knew that stuff fell, and I don't know exactly. I don't know if anyone knows exactly what made him figure it all out, but
Yeah, like
yeah,
I mean,
he was able to.
he's seen as like
Yeah,
right
I
one
mean,
of the
it
biggest
was really
guys in
like-
physics. Yeah.
Oh yeah, I mean, he did a lot of stuff too. It's not like he that was his. Yeah, I mean, the whole field of classical mechanics itself really stemmed from him.
Mm-hmm.
He had ideas about light as well that were influential.
Optics, right?
for,
He did a lot with optics.
Yeah. And he actually also was heavily into alchemy.
Oh, I like alchemy. I'm a fan of the gold.
Yeah.
You know?
So
Really?
he actually died probably of mercury poisoning
Oh no.
because he was attempting alchemy experiments, and yeah. So he some people describe him as the last magician.
The Last Magician.
Because
Oh, that's so cool.
before then, alchemy was the precursor to science. So
Mm-hmm.
once that it kind of he was kind of the last magician. So
That's cool.
Galileo was figuring out some certain stuff, and eventually Newton was. I mean, so what was cool about his theory, it was kind of unified in the sense that it unified how gravity works on planet Earth as well as what happens out there in the planets.
Yeah, that's what we talked about, right? That we need the laws of physics to hold for like all points in time and also all points in space.
Right.
Because otherwise,
And
like,
so if you
everything
look
messed up.
exactly, and so if you look at the history of physics, it started as a bunch of different stuff, right? You have electricity, you have magnetism, you have light, you have gravity, and so there should be one theory one day in principle that could describe everything, but we have thermodynamics, we have fluid dynamics, and they're all different, right? But over time, more and more things kind of get unified together. So James Clerk Maxwell, he came out with this theory of electromagnetism and discovered that light is an electromagnetic wave. So that was kind of, I would say Newton and Maxwell are kind of like the two.
They're the
greatest
G's, the
physicists.
OGs of physics. Yeah. Woo,
And then
I actually
Einstein.
have a good question. Yeah, who do you think's the greatest modern physics? Einstein? Yeah.
Well,
about Feynman?
What do you mean by modern? What do we mean by modern?
Yeah, that's a good question.
Like alive or?
Oh, yeah, good.
of
Yeah,
the-
so
of the
let's do
1900s?
let's say 1900s, and who do you think the greatest physicist alive right now is?
Alive.
Yeah.
I mean, I have these like special heroes of mine. I really think Hagen Kleiner is amazing.
Hagen Kleiner? Okay, cool.
He figured out some stuff that Feynman couldn't figure out.
What's his name? How do we spell it?
Hagen space Kleinert.
Oh, Kleinert.
Like if
Oh,
you
there
just go to his website,
Is it this guy?
and just Google Google his name and find his website. Like it's almost like he's so good that people are just like, oh, okay, yeah. Like he doesn't get the recognition. It's like I'm kind of like an underdog. Like I like finding these people that I think are brilliant that people aren't really talking about.
Does he have a Nobel
I mean,
Prize? He's got a Max
No,
Born
no.
Prize. Yeah. Okay.
So he has this 1,000-page textbook on he's written all these books. Like it's just so impressive to me, just
Yeah.
how prolific he is. That
Very
path
cool.
integral book is 1,000 pages.
This one right here?
It's
Wow.
mind blowing. Yeah,
Wow.
and so when I haven't read all of it, of course, but he has this story that he talks about when he Feynman was trying to figure out the path integral formulation of hydrogen, and he couldn't figure it out. And so he went to Hagen Kleiner he said, I think you should figure it out. And
Yeah.
it took him like 15 years, but he eventually was studying condensed matter, and he was looking at these defects in condensed matter, in solids, basically, in crystals and stuff. And then he realized how that related to this torsion, which is a form of gravitation. So he was able to see this analogy between matter and space-time
Yeah.
and figure out how this exotic form of gravity is needed just to describe the path integral of hydrogen. And it's
Spin
just
coupling to self Kleiner. What's this thing he wrote on the last blackboard or something?
Oh yeah, I don't even know. Oh, is
That's
that
good. Oh, that's what I'm trying to zoom in on.
yeah, I don't know. Yeah, I forget what the pictures are, but
Spin coupling or something.
yeah,
Okay, put it
so
on-
I like him a lot.
That's cool.
I don't know. Yeah. Let's see. I mean, Nima Arkhani Hamed is really good.
Yeah, he's a very good guy.
Yeah.
Nice. Let's see. Teacup, could you share with us a practical example of how theoretical techniques used in the LHC can be applied to the laser interferometer? Oh, to LIGO. LHC and LIGO connection.
Yes. So, it's really about the fact that you developed a lot of scattering techniques for scattering particles.
Mm-hmm.
And so when you do, and it's cool because with the LHC you have all these quantum effects. So that you have these Feynman diagrams that have the loops and the perturbation theory.
Yeah.
And so these proton collision, the protons are made of quarks, and the quarks have color charge, and those color charges source gluons, which is the force carrier of QCD, or the strong force, quantum chromodynamics. So it turns out that my advisor had found this method called the double copy,
right,
that allows the gluons to get mapped into gravitons.
Okay.
And so now it turns out that it works for quantum gravity as well, which is cool. But with LIGO, quantum gravity doesn't really matter right now. But we can't even solve these things exactly. So historically, the problems necessary to predict what is happening for these gravitational waves, it's so difficult. No one can do it. You need to, like, analytically, no one can do it exactly. You need to do approximations. And then there was this whole development of numerical relativity. And so the numerical relativity has been being developed for 40 years, if not longer. And so that's kind of like the leaning way to do things because they've been going at it for so long.
Mm-hmm.
But, as the LHC, the theorists are kind of getting scared because it's like, okay, we found the Higgs boson. That's why they were built.
Yeah.
The LHC was built. So now what, right?
So now
you can't
what?
Just keep claiming we're going to find supersymmetry when you're not. It's not going to be found. So
I see, but they need funding. They need to keep the lights on. So like, what can we do?
Yeah. So what he realized is that, well, there was some paper they put out. It was funny. So they put out this paper of applying the double copy to gravitational radiation. And I should mention there's also approximations you can do on the gravity side. It's called the post-Minkowski expansion. When you do that, you can get this Taylor series or perturbative expansion. So it actually blew my mind to realize that, I had always learned these Feynman diagrams with the loops is for quantum corrections. But in classical physics, you can use these Feynman diagrams with loops for corrections in gravity as well in this post-Minkowski expansion. And so what you're expanding around is fluctuations in the metric, because you have Minkowski spacetime, and that's in special relativity. And then it's this nice simple 4x4 matrix with it's all in the diagonals, and you have like a -1 and 3 1. So it's almost an identity matrix. And then in general relativity, that gets generalized to this space-time metric that can be whatever, and it's dynamical and it's super complicated. But what you can do is assume a background metric and perturb with small fluctuations around that background metric. And that sets up this perturbation theory. And there you can still use the same loop diagrams from the quantum field theory to discover, to calculate classical gravity problems. And furthermore, what I was tasked to do was to figure out how the double copy works. So we can double copy from classical QCD to general relativity. For, it's not like I was doing anything that LIGO will use tomorrow, but, it's like developing the methods that, after other people build on it for a few years, then maybe it can get competitive with the numerical relativity in certain instances. So, and it was at that time, all the people working for him didn't want to work on it because it's like, they all, they're studying particle physics, and now you want to do gravity? That's completely different.
Oh, yeah.
And so no one wanted to do it, and so it was like, I had to do it, or I was willing to do it because he wasn't really giving, like, I was like, okay, you want to work on this, I was like, well, I'm waiting for some, I need to do something. So yeah, it was really stressful doing that project because I had to figure out how this other paper worked, and then I started talking to them, and they're like, I'm trying to okay, like, how does that work? How does this work? It got to the point where one of the original papers that I showed that it was like they calculated gravitational radiation, for the system that couldn't radiate anything. So I was like, good job, guys. You guys calculated 0 maps to 0. Great job. You know, and so like the authors of the paper were like, oh, like we figured it out. We got the double copy. And I'm like, you can't, it only works for a single black hole. Like the entire formalism you have only works for one star. And you need 2 things to interact to get these gravitational waves. And it took me forever. And like finally I'm like at the chalkboard with this other graduate student. And then it finally was just like, oh, you're right. And I was just like, yeah, like what you're doing is useless. So then I was my advisor was telling me to like use that to build on it. And I was like,
but it's just useless.
Like,
it's useless. You know? Yeah,
like,
it doesn't work.
And so then he's like, figure it out. So then
you'll figure it out, dude.
I figured out something that worked with electromagnetism and linearized gravity because and it would work. And then my advisor was just like, no, it's not the double copy because the double copy works for nonlinear stuff, blah, 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 blah. It's QCD. And then I was just like, and so like he like, it was strange. They got a caseworker involved. They were trying to kick me out of school for not performing. And so they had this caseworker come in.
Yeah.
And he's like, okay, so
how does a caseworker even understand what's going on at this point? Because you're always speaking like gobbledygook to this caseworker.
So he's like, okay, so you're getting a PhD in theoretical physics. I see you have a GPA of 4.9 out of 5.
Yeah.
What's the problem here, right?
Yeah,
like the best thing you could find. It got to a point where like I was a little
You're rambunctious.
Like,
you're rambunctious at points. Yeah.
I boxed an equation in one of his textbooks.
Yeah.
And it was like, it's like, you can't do that. You know, that's my textbook.
Oh, what, like you're being aggressive or something with it? Like what?
I put a pen mark in one of his textbooks and I boxed it. And so the caseworker was like, yeah, you should have put a Post-it note next time. And I was like,
dude, stop.
You know. So it was like they literally purposely changed the rules
afterwards,
just so
probably,
I couldn't
right?
get paid. So it was like you only TA a certain amount, and then it's kind of like customary for your advisor to pay for you.
Yeah, the GSR or something.
And so it's kind of this gray area where, but then like you can get in your last year if you apply for this thing, you can get some money through school
deferral or something
if you're working on your thesis.
Yeah.
And so I purposely I TA'd for this class where it was like it didn't count towards that quota, and I did it purposely as a safety because I could see what was happening.
Yeah.
And then I figured out the rules and I was like, that's the rules. And then like the professor who's the academic advisor was like, nope, that's not the rules anymore. Like that doesn't count. So you can't like, and I was just like, what? And then
but they changed
I
the
want to go
rules.
into the other drama too, but
it's okay.
My advisor had just gotten this huge $11 million donation. And then he's like, I can't pay you.
Oh, what happened to him? 1 sec. Maybe his laptop died. 1 sec. He's coming back. Oh, let me get you back on stage. There you go, DC. You're back. You're good.
Yeah, so it was a stressful experience because they were trying to kick me out of school as I'm trying to figure out.
Yeah,
how
while you're just
works.
trying to do good stuff, like, dude, that's fucked up.
And
They switched all the rules.
So it was rough, but I'll leave it at that because I don't want to. At the end of the day, like I don't have any regrets. I don't have any bad blood with anyone there. I mean, that's just the politics of the situation. I should have known better at the end of the day. It was a learning lesson for me. I was purposely pushing people's buttons.
Well, you told us you were having fun experimenting, right? You were being like, I can get them to say things.
Well, no, but I was just honest. I mean, at the end of the day, I was just trying to learn the truth. I saw it as a big problem. It got super, like, it turned out, it was like, damn it, it turns out it's related to global warming. Like, this like, the only information on the internet, it was like, I was like, I don't even care about that. Like, I was just trying to understand, like, how does this physics work? Like, how does gravity and thermodynamics come together, with that experiment? And then, so what ended up happening is someone else kind of scooped me and they put out a paper that kind of made it work. So then I had to learn their stuff, and then it kind of did like a cousin theory that built on that and built on it. So I was able to finish my PhD. So
it
was a good
experience. You made it through, dude. Yes, we're survivors, dude. I mean, amongst our class, right? I think we had like 30 students come in, right? We were like 30, right?
But it was definitely, I don't know, 28 something. Yeah, 20, it was definitely high 20s.
Right, but 30, I only think like half of us graduated, probably. Right?
Yeah, it was weird seeing people dropping off because it's like, right, and so it's like every level. I mean, with academia, especially in like I
It's
don't
a
know,
pyramid
physics
scheme.
and especially theoretical physics. Well, right. It's like you go to undergrad, then all they graduate, then you have to go into grad school, then you get a postdoc, and then you become a professor. And at every level, it's just like weeding out and weeding out. So
Yeah,
it's
it's nuts.
it's an undergrad. It's it's kind of cool. Like no one's like dropping out of school that much.
Right.
Maybe it'll happen a little bit, but then like in grad school, it's just like, I mean, we're at a
man.
good school, and
Yeah.
there's a smart people like who got, other people who were smart got rejected,
Yeah.
and like these people are dropping like flies. It was like,
Yeah, I was just
it's
like,
like this intense. It's like, wow, like they literally make this test.
Yes,
you have
to fail
pass it to
30%.
continue on,
And but they
literally
purposely fail it.
30%.
Yeah.
It's just like weeding out, and it's rough, yeah. But if you can stick it out, I mean, you come out that much stronger, right? You're honing your skills, and you really can just solve. You're good at problem solving in ways for even if you don't stay in physics. That process builds a lot of character.
For other things. Yeah, it builds a lot of character. The hottest fires make the strongest steel, that type of thing. Nice. Good question from Teacup. Let's see what we got next. Did we do this? I think we did this. Oh wow, we've done all the questions. Oh, very cool. Yeah, we went through all of them. For Horizon has a quick question because he didn't get it in time to submit it. Said if you could go back to your teenage self, what's the one thing you would tell yourself and why? It's always a fun one. Like, what would you tell your teenage self?
Oh man.
Buy Bitcoin.
Yeah, honestly, I'm not gonna lie.
Bitcoin.
Because I was one of these people that I knew about Bitcoin super early.
Yes.
And I was all into the theory of like, oh, smart contracts and this and that. But for the longest time, I did not put money in. And like, that's honestly like, that's a good one because I was kicking myself. I eventually did make some money in crypto a few years ago.
Yeah.
But it took me a long time. Yeah, honestly, it's just like, hey, just put $50 in Bitcoin. Get buy Bitcoin.
Buy 5 Bitcoin, dude, for like $2. You'll be fucking set.
That's a good one. Because honestly, that's such a once in a life, not even once in a lifetime, like once in a century.
Couple lifetimes,
like, that's never gonna happen like again like that. But something more practical, like I think it would be kind of, even though I was the type of student who asked a lot of questions, I think it might be like, as I go into college, take advantage of the opportunities that you have as you have them in contact with people, because as soon as you're out of school, or even just like networking and meeting people and having friends, because like once you're an adult, like it's hard to meet people.
It sucks, dude.
Hard to make friends.
It is.
And also,
it's hard
even
to
the
keep
concept
friendships.
of like burning bridges. Like I was a nerd growing up. I kind of got made fun of, so I came out of my shell. I eventually kind of figured out how to be cool in my own way or whatever. But so I had I didn't really have good friendships. I was able to make some friends, but I didn't have really close friends. So I would kind of like, I would go to summer camps and just kind of be annoying and like sort of make friends and then not stay in contact with people. Like I didn't really build lasting relationships.
Yeah.
And I kind of looked at it like, oh, well, I'm going to be done with high school. I'm going to go to college anyway. So like, what's the point,
Right.
But, and then I kind of did that in grad school. I went to grad school and then I didn't really talk to any of my friends from college. And now like I talk to Gio, but like now I'm an adult and like I joke like Gio is my only friend. That's what I tell him. 'Cause it's just like, I'm not.
Sometimes that's all you need,
so.
though. It's all you need, dude.
Yeah, exactly. But I mean, I think you gotta look at the long term and realize like you could meet someone at a young age where they could change in 10 years and go down a different path, and like having that connection, it could come in handy in ways that you never know. So just keep doors open, stay in contact with people when you can, have genuine friendships and step in that, because that's something I didn't do that I wish I had figured out better.
Yeah.
And also, when you're in that moment, if you're in high school or if you get to college, like just realize like you have access to these people and that's going to go away. So take advantage of that.
Yeah, go to office hours, kids. That's what I do with this whole Discord.
Yeah.
I kick myself. I never went to office hours. I never went, and I really should have.
That's the thing. I mean, you could be the student, even if you could go to college, and it's kind of this freedom. You could just not go to class and get good grades. But I mean, it depends what you want to do. If you're just like a computer whiz and you're just doing your computer code and you want to just get a job and you're good, I mean, that could be fine. But like you have this resource, they're there, and you could take advantage of it. And you might later be like, wait a second, I didn't even realize, or like research. Like I took quantum field theory in undergrad. I was able to take these graduate classes, and it didn't really occur to me that it's like, wait a second, like I'll be doing research one day, and like if I had kept a better relationship with him, I could contact him again. But
Yeah.
I kind of like burned a bridge by asking too many questions in a way, and
Too much poking.
Yeah. So it is what it is. But yeah. I guess that's what I'd recommend.
That's cool, dude. I like that. Yeah, that's, you never know when people are gonna, I guess, come in handy later, right? I even see this now with like my today, like, and that's what I have this whole AMA for is I started realizing, wait, I have some really awesome people that I call my friends, and this is a super useful way to get them a platform to talk to the youth and stuff. I'm like, wow,
and that's what having faith is supposed to all be about. It's like, you don't know, you can't predict the future, and now, faith is like a religion thing, and now religion's kind of not, it's kind of dying, but now I feel like it's leaving society. It's like they're trying to replace science with religion, but science isn't meant to replace, it's different. And so, just if you're in a situation now where it feels like it sucks, it's really boring, just like remember that what you do now will affect what you can do in the future, and things might change in a way that you're not going to see. And so you could just kind of have a nihilistic attitude and be like, oh, what's the point of anything? But no, even if what you're doing seems stupid now, just keep working hard and getting as good as you can, because later it will open some door to do something that you like that you didn't even realize was possible.
Yeah.
You're not going to be able to predict it.
Create your own luck, dude. Just keep creating luck. Opportunities for luck to happen.
Yeah, and that's the thing. You need to, it's like a lot of people that are like, oh, I just got lucky. But it's like you do the hard work so you can get lucky,
Yeah.
And it is kind of both. You do kind of need to do hard work and get lucky. But if you don't do the hard work and you just get lucky, it's like chances are it's not gonna, it's like, oh, I found a parking spot, but it's not gonna do for you. You know what I mean?
It's sometimes a very hard thing at Costco, dude, on a Saturday.
Yeah.
Nice. Okay, one last question, because a couple of students kept asking this all the time. They said, how do you get that epic beard of yours? That epic mustache beard thing, dude.
I just, it's really about the mustache. My beard isn't that epic, but
the mustache.
Growing it out. Honestly, the thing is, you can get into beard wax. None of it works.
None of it works.
You gotta get basically African hair products. So they have edge control, it's called.
Okay.
And that's what they do to get their baby curls in their hair. That stuff works way than any mustache wax you can get.
Edge control.
That's
like this stuff? It's this stuff?
Yeah.
Oh, wow.
Yeah, so it's kind of like gel, and I just, after the shower, just wait, dry off a little bit, but keep it a little wet, and then just do my thing, give it a little curl.
Do your thing, dude.
I've just been, it's kind of, you kind of have to grow it out, and you get through this, awkward
There's this awkward phase. There's always an awkward phase.
But it's not that awkward either. It's not that bad. But, yeah.
One of the students says, "Can we meet and greet your cat real quick? I see in the background, little floofball. Is this cat?
Yeah.
Is this friendly? This cat? Athena?
Yeah.
What's up, Athena?
And then I also got Timmy the Puma down here. Yeah, so you got Athena and Timmy right there.
Oh, that's so fun.
On the little cat tower. I don't know if you can hear them meowing. They're like, oh, I know where they want to get fed. They're like,
oh yeah, well we have been streaming for a while. We haven't, dude. 3 hours and 27 minutes. Wow, we've been going for a while. That's all the shit there's too. Nice. All right, cool. Let's last part of the podcast I always do is I give out a prize to whatever kid had the best question. So you can either pick if there's one that sticks out where you're like, that kid did the best, I love that question. We can do that.
It's hard for me right now. I thought a lot of them were good.
If you got a couple contenders, I can run it on a probability wheel, is what I can do. You can
it's
pick,
also hard
top
for
three.
me to see. Let me see.
Here,
let
me
me double click. There we go. I figured it out now.
Or I can give you the link.
I double clicked on the screen, so now I'm actually
Oh, okay. There's a lot. I think.
I mean, Saint was pretty good. Let's see. Let's keep going. Wait, what's this? I like the ones where they ask a lot of questions for some reason.
Yeah. It's too funny. I always have the guest pick because like I don't want the kids to start like finding out the method for what I think the best question is. But we always have a new guest every time, so it's kind of like on their toes, like what it is. Yeah.
Well, yeah. Let's scroll up again. I mean, Taco Cat's pretty good as well. Jamarcus is good, but Dark Aspect was okay as well. That was a great one. No, I shouldn't say okay.
He's just okay.
But I think I'm gonna go. I think I'm gonna go with Saint. I don't know why. I just something about it. I think it was genuine.
Yeah,
it's the right
upcoming college students. Yeah, nice. Good job, Saint. You've won. Okay, let's thank our guest, David Chester, Dr. David Chester, for today's Golden Hour AMA podcast.
Thank you for having me.
Yes, thank you, dude. I really appreciate it. Yeah.
This was a lot of fun.
Yeah, awesome. Yeah, this is great. Yeah. Okay, our next stream is going to be on Monday. That'll be at 3 p.m. Pacific, 5 p.m. Central, 6 p.m. Eastern. So come on by then if you want some help with homework. If you have any other questions for Dr. David Chester here, he's in our Discord. I think he's David Quantum Gravity is his username. So send him a DM or something. I'm sure he'd be happy to talk to you guys. Hopefully we'll see more of you with all the fun AI stuff we're going to work on.
Oh, yeah.
Oh, yeah.
It's
all right.
been a pleasure.
Yes, awesome. Thank you guys for coming by. We'll see you on Monday. Peace out.